as post pruning and pre pruning in decision trees. Now, just by the meaning of pruning, I think you will be able to understand something at least. Okay, so let's discuss what exactly is this post pruning and pre pruning, and let us understand why do we do post pruning and pre pruning also. So guys, suppose if I have a training data set and if I probably use a decision tree for this particular training data set, so and if I use the by default parameters that are available in decision tree, it will start splitting it and it will make sure that it will keep on splitting unless and until we don't get the leaf node. Okay, so let's say here I'm actually getting the leaf node. Unless and until we don't get the entire leaf node, it will keep on splitting, right? So this is also a leaf node, but here we quickly got that specific leaf node. Here till this particular path when we went, here we got the leaf node. Now let's consider that at this particular instance, if I have 9 years and 2 nodes as my output category that is remaining, and what did I do? I did a further split and made sure that I get 9 years and 0 nodes. And since this is an impure split, and here I probably got 0 yes and 2 nodes, right? So here this also became a pure split and this also became a pure split, and finally I was able to get a leaf nodes like this, right? So this is also a leaf node and this is also a leaf node. Now understand something about pruning, okay? Pruning, whenever we talk about, right, you've seen gardener, whenever some plants, they grow, right, they just try to prune it so that the shape is maintained and it grows in a proper way, right? So similarly in decision trees also, whenever I try to do this kind of split completely to its depth with respect to the training data set, usually we face a scenario which is called as overfitting. Now, many times I've discussed about overfitting. Overfitting basically means your train accuracy, it gives very high because we have done the splitting completely till the end, but with respect to the test accuracy, my accuracy will be very, very low. Okay, so this scenario we basically say it as overfitting, and with respect to overfitting, again I'm repeating it, you usually get a scenario of low bias and high variance. Bias is for training data, variance is for test data, right? Since over here the test accuracy is low, so I'm saying it as high variance. Okay, now if I'm splitting my decision tree completely to step, I usually face an overfitting scenario. Okay, now how can I prevent this overfitting scenario? Because if I'm using the default parameters, you'll be able to see that I'll get my all decision tree will get split completely to step, right? So in order to reduce the overfitting, we can use two different techniques. In order to reduce overfitting, we basically have two different techniques. One is specifically if I talk about this overfitting, in order to reduce it, one technique is called as post pruning and the second one is pre pruning. Now what does post pruning mean? Post pruning basically means first of all I'll construct my complete decision tree, and then after that I'll start pruning it or cutting it. Okay. Now in this particular scenario, let's say at this particular depth, I was having 9 years and 2 nodes, and still I made this further split. Okay. But just understand over here in this scenario, the number of output categories is 9 yes and 2 nodes, and obviously the ratio of yes and no in this particular case, the ratio of yes is very high, right? Over here because you have 9 yes and 2 nodes, very small number of nodes and yes. So I did not have to do the further split because whenever over here if it comes, right, whenever with respect to all this decision it comes over here, I should have selected okay my output is basically yes, but still I did this particular further split. So in the post pruning, what we can do is that we can basically cut the branch from here itself. Because I don't want to further do the split. Till here only, I should be able to get, since the maximum number of yes is there when compared to no. So I will say that, okay, I consider this as my leaf node and it will basically give me the output as yes, right? So this is what happens in post pruning. Okay, in post pruning, what we do? In post pruning, we first construct the decision tree. And then in the second, we prune it with respect to depth. Okay. And why do we prune it? So that it does not, lead to overfitting scenarios. So in this scenario, the overfitting will not happen there. Then for the test data also, it will be able to provide you the generate output. Okay. So this is the one. What about pre-pruning, guys? Okay. And one more thing about post-pruning, post-pruning should be applied for smaller data sets. Okay. Because just imagine if I have millions of recordings, if I start creating decision tree till the end, it is going to take time, guys. Right? Whenever we have smaller data sets, and like once we construct the entire decision tree and then we prune it, then the time complexity will be high. Right? So we should definitely use post-pruning for smaller data sets. Now what about pre-pruning? Now what does basically pre-pruning mean? Right? Now pre-pruning basically say that while you're constructing the decision tree, okay, you don't have to construct the decision tree entirely, like how we did it with post-pruning. While you're constructing the decision tree, you can play with some of the parameters. And yes, in decision tree, you have some of the parameters like max features, right? You have some of the parameters like depth, max depth, So these all parameters are there, max depth, okay? And there are also some more parameters with respect to the split. How should the split happen? All these features are basically some of the hyperparameters, okay? So here, in short, in pre-pruning, what we do, we play with the hyperparameter. We tune with hyperparameter while constructing the tree. We tune with hyperparameter, or I can also write this as hyperparameter tuning while constructing decision tree. Hyperparameter tuning while constructing decision tree. This is super important. So that basically means when you are constructing a decision tree, you can basically play with all these parameters, and through the hyperparameter tuning, you will probably be able to get what should be the max depth. What should, let's say max depth is 3 or 4. What should be a max number of features that you should probably take? The different parameters. And if we refer to sklearn, we'll be able to see all the hyperparameters that are actually used. Okay, max depth is there, max features is there, and there is also something called a split ratio and all. Okay, so let me do one thing. Let me quickly open the decision tree classifier algorithm and probably show you that specific part in the specific basically we're just going to see the sklearn documentation, right? So if I go to sklearn decision tree classifier, just search for it. Here you'll be able to see that I'm getting an sklearn, and here you'll be having many features, right? So what are features you can play with? One is criterion. You can use Gini, entropy, log loss. Okay, log loss was a part of logistic regression, if you remember. Then you can use splitter, like what splitter should be there, best or random. Max depth is one of the features. You can play with that as an hyperparameter, and we use grid search CV for doing it. You have minimum sample splits, you have minimum samples leave, you have minimum weight fraction, maximum features. So all this kind of hyperparameter, you can play with it, and you can hyperparameter tune it. So when the construction of the tree will automatically happen, this parameter can be set initially, and your decision tree can be constructed, right? So yes, this was it to make you understand the differences between post pruning and pre pruning. Or most of the things will be shown in the practical part. You don't have to worry about it. Here we just understood the maths in-depth intuition. Okay, I'll see you in the next video. Thank you. In this video, we're going to discuss about decision tree regressor. In our previous videos, we have completed decision tree classifier. We have got to see that how classification problem statement can be solved using decision tree classifier. We have learned about entropy, information gain. We have understood about post pruning, pre pruning, and many more things. Now, similarly, decision tree can also solve a regression problem statement. Now, what do a regression problem statement basically mean? Here you can definitely see that our output feature is basically a continuous feature, right? Now, whenever our output feature is a continuous feature, at that point of time, I usually use a decision tree regressor. Obviously, in decision tree classifier, we used to do some kind of splits. Whenever we do some kind of binary splits, we actually say it as cart technique of decision tree. And similarly, we will be making this kind of splits. Now, during the splits in decision tree classifier, what we used to do is that we used to use techniques such as entropy, entropy, Guinea impurity, right? Guinea impurity, and we used to also use something called as information gain. Entropy and Guinea impurity is basically for the purity split. Information gain is basically to find out which feature should I use for making the split. Now, decision tree regressor, I cannot use this because whenever we are using information gain or entropy or Guinea entropy, our output feature was actually it was a fixed number of categories. It can be a binary classification or multi-class classification. So with respect to decision tree regressor, we are going to see that how we are going to make a split for this. So let's take this particular example. I have a data set which has experience, gap, and salary. Now, based on this experience and gap, my model needs to predict what should be the salary. And this gap is nothing but career gap. Suppose if the person has career gap, obviously the salary may reduce a bit. So this kind of model will try to create a decision tree model, and we'll try to solve this regression problem with the help of decision tree regressor. And then we're going to understand how does decision tree regression work. Okay. So let's start with, I'm just going to take this continuous feature and probably make two splits. Okay. First split, I want to make sure that I keep threshold value this one, and the second split, I probably keep a threshold value this one. So what I'll do is that two splits initially will start with less than or equal to 2. So here I'm going to get one split, other split. Okay. Whenever it is less than or equal to 2, if this is true, I'm going to basically say yes, no, it'll come here. Now with respect to this, how many different outputs I have over here? You can see 40k is my output that I'm getting over here, right? Now similarly, if it is no, then what is the remaining output that I'm getting? I'm just going to write it down. Okay. And this is what we did with respect to the classification also, right? So here is my 42k, 52, 60, and 50. Okay. Now this is the first split, and similarly, let's say that this is my first split, and now I'm going to change my threshold to 2.5. So let's say now I'm getting a new threshold with respect to less than or equal to 2.5, and I have similar two kind of splits over here, which is this one and which is this one, right? Now let's say in this split, if I'm saying less than or equal to 2.5, that basically means I have these two values. So I'm going to do 40, 42, and this will be 52, 60, 56. Now remember, our output feature is continuous. Now obviously, if I really wanted to compare between these two splits, which one to select, whether I should select this value in the feature or this value in the feature, we used to use information gain in classify. But here we cannot use it because finally our output is a continuous value. So how should I basically check whether this split should be selected or this split should be selected? So we are going to use something called as variance reduction. Okay, variance reduction, specifically in case of regression problem statement. Now I'll talk about it. What is this variance reduction and all, and we'll try to discuss it with formula, so you don't have to worry about anything. I'll try to cover everything. So in variance reduction, first of all, we need to compute variance. Okay, and I hope everybody knows the formula for variance. So I will just provide a definition: summation of I is equal to 1 to n y minus y hat whole square. This y hat that I'm basically writing, it is nothing but average, right? Average. And if you have seen this in linear regression, and also we basically say this as mean squared error, right? So we are basically going to compute the mean squared error for each and every node, and then we're going to combine them to actually find out the variance reduction. And then finally, out of these two splits, whichever has the maximum variance reduction, we are going to take that specific split, and that is how it is basically used. So in short, if you're using decision tree regressor, we use instead of using entropy and information, entropy or Guinea impurity, we use something called a mean squared error. Okay, so this is how it basically happens. Now what I'm actually going to do, first of all, I'm just going to go ahead and compute y hat. How to compute y hat? Just go over here and try to find out the average. So here, if you take 40, 42, 50, 60, 56, you will be getting 50k. Okay, so I've already done the calculation, so I'm directly writing it over there. If you probably find a mistake, you can let me know in the comment section. Okay, so here it is. Now what I'm actually going to do, let's go ahead and calculate the variance for root for all the child nodes also. Now in this particular case, my root will have all my output values like 40k, 42k, and I will be having 52k, 60k, and 56k. Okay, similarly over here also I'll be having all the values like 40k, 42k, 52k, 60k, and 56k. Okay, so I have all my values over here with respect to the variance. Okay, now let's go ahead and calculate the variance of root. Okay, so first step, we are going to calculate the variance of root, and then we'll calculate the variance of child node. Now in order to calculate the variance of root, what I'm actually going to do, first of all, in this particular root node, how many values are there? So 1, 2, 3, 4, 5, right? So 5 values are there. Now obviously what I'll write 1 by n as 1 by 5. And then here you have summation of 1 to 5. 1 to all these particular values, 5. So y minus y hat, what does this basically mean? Y minus y hat basically means I'm going to basically consider each and every feature, like 40 minus y hat is nothing but 50. So that is what I'm actually going to do. So here, let me write it down, y minus 40 whole square. Okay, this is my first one. And then we'll go and do it for 42k. So I will just go ahead and write 42 minus 50 whole square. Then my third number is basically 52k. So it is nothing but 52 minus 50 whole square plus, well, after 52, I have 60 and 56. So 60 minus 50 whole square. And after 62, so this is my 52, right? Okay, 52, 60, and 60. And then I have 56. 56 minus 50 whole square. So I'm just going to compute this. Now in order to compute it, I can basically write 1 by 5. I will be having 100 over here. This will be 64 over here. And this will be 4 over here. I hope I am doing the calculation right. If I'm getting it wrong, you can let me know. Okay, so these are all the values that I am probably getting it. And if you probably use a calculator, you will be able to see the specific output over there, and we'll be able to see the value. Just go ahead and quickly calculate it, use the calculator. But according to my calculation, I've got 60.8. So here, in short, for variance of the root in this particular case is 60.8. In this case also it will be 60.8 because both are having this number of outputs. Now let's go and compute the variance for this child one. Okay, so child one for the first one. So here I'm just going to compute variance of child one, that is C1. Then again, I will basically have formula 1 by m, summation of I is equal to 1 to n, y minus y hat. This is nothing but y mean. In short, here I'll be having 1 by how many numbers I have actually with respect to n. Over here, only one number, right? So only one number is basically here, so I'm going to just use 1, and then this will be summation of I is equal to 1 to n. No need to write this again and again. So this will basically be 40 minus 50 whole square because my y mean is 50. So 10 square is nothing but 100. So variance of child 1 over here is specifically 100. Okay, so variance of child 1 is nothing but 100. Okay, now what about variance of child 2? Variance of child 2. So variance of child 2, let's go ahead and compute it. So here I will be having variance of child 2, and this will be nothing but 1 by n, summation of I is equal to 1 to n, y minus y hat whole square. So how many is the n value over here? I have 1, 2, 3, 4, right? So 1, 2, 3, 4. So this will be 1 by 4. Okay, and here you can start. First number is what? First number is 42. 42 minus 50 whole square. 52 minus 50 whole square. So I'm just going to write 42 minus 50 whole square plus 52 minus 50 whole square plus 60 minus 50 whole square plus 56 minus 50 whole square. So you just go ahead and compute this, and obviously I'm just directly seeing my notes over here so that I don't want to spend much time with respect to quickly doing all those things, right? So let's quickly see how much did I get. And then we'll just go ahead and write the variance of child 2. So if you do this particular calculation, it will be nothing but 1 by 4. Here it will be 64 plus 4 plus 100 plus 36. So in short, you are basically going to get somewhere around, let's see the calculation. 64 plus 4, 68, 168 plus 36, 204 divided by 4, which is nothing but 51. Okay, so 51 I'm actually getting over here. You can do the calculation with respect to this. I just want to be accurate, so I have done this calculation. So this is what is my variance with respect to C1 and variance with respect to C2. Now what I'm actually going to do is that once I compute all the variance with respect to root node with child, I'm going to apply my variance reduction formula. So my variance reduction formula will be something like this, which will be nothing but variance of root minus summation of weights of I, and then this will be variance of child. Okay, now let me talk about this one also just in some time. So what is the variance of root in this particular case? It is nothing but 60.8. So here I have basically 60.8 minus W of I. What is W of I? Now you need to understand what is W of I. First of all, we'll go with respect to the left node. Now in this particular case, you can see that after the split, how many are there in the left node? Only one output is basically there in the left node, right? 40k. And before we had how much? 1, 2, 3, 4, 5. So if I try to find out the ratio, that will basically be giving me the weights. Now in this particular case, since I have just have one element on the left node, I'm just going to basically write the ratio as 1 by 5. Okay, so that will be the ratio with respect to my variance node. So 1 by 5, and then I will be multiplying it with my variance of child 1 on the left hand side. So it is nothing but 100. So here I'm just going to use it as 100, and then I'm going to do the summation. Similarly, what will be the right hand side? You can see 4 elements are there, so I can definitely write 4 by 5. So this is basically my 4 by 5 multiplied by what is the variance of child with respect to this child? So it is nothing but 51, right? So this is my entire calculation. Now I can go ahead and just calculate it, and finally you'll be seeing 60.8 minus 20, and probably I'll just see my notes again so that I can get the calculation quickly, because I don't want to do the calculation again and probably make a mistake on the same, right? So let's see. So quickly, let me just do this. I'm just going to open the calculator. It is going to be 60.8 minus 20, 10.2, so 40.2. So it is also going to be almost similar thing, right? So let's go ahead and calculate it. Okay, I'm just going to use my calculator. It's good. So let's open the calculator quickly. So I'm going to open the calculator, and this is nothing but 4 divided by 5 multiplied by 51. Okay, so this is nothing but 40.8. So this is minus 40.8, which is nothing but 60.8. So here I'm going to get 0. So in short, the variance reduction with respect to the first split, I'm just going to write it over here. The variance reduction with respect to the left split, variance reduction with respect to the left split is 0. Okay, so this is for the left one, left split that we made. Okay, similarly, let's go ahead and compute for this particular split also. Now for this particular split, I can do the same thing. Already I found out this. Let's find out the variance of child 1. So child 1 over here, I'm just going to use 1 by 2 because there are two nodes on the left, and then 40 minus 50 whole square plus 42 minus 50 whole square. Okay, so this is there. So 1 by 2, 100 plus 8 is 64. So here you'll be able to see 164 divided by 2, which is nothing but 82. Okay, so 82 is what I'm actually getting with respect to the first leaf node. So let me just compute it. Yes, it is perfectly fine. And similarly, if I really want to calculate with respect to this node also, what is the variance? So I will go ahead and calculate variance of child 2. Okay, and this will be 1 by 3 since I have 3 nodes, and here 52 minus 50 is nothing but 2 squared, so 4. This 60 minus 50 will be 100 because 10 squared, and this will be 36. Okay, so finally you can see that I'm getting 140 divided by 3. So let me just open the calculator and let me write it down. 140 divided by 3. So this is nothing but 46.66. Okay, finally if I go and compute the variance reduction, okay, it is nothing but, or let me just compute the variance reduction. Then I'm just going to make a split over here so that I don't intermix multiple things. Okay, so let's go ahead and compute the variance reduction of the right node of this right split, right? So here I can basically write nothing but what is the root node? It is nothing but 60.8 minus summation of how many elements are there in the left hand side. There are two elements, 40, 42. So what I'm actually going to do, 2 divided by 5, which is going to be, since I'm going to use that specific weight, multiplied by what is the variance of this particular node? It is nothing but 82. And finally you'll be able to see plus. Finally here is 3 nodes, so I'm going to basically use 3 by 5 multiplied by 46.66. 46.66. Now if I go ahead and compute it, it is nothing but let's open the calculator quickly. So here you'll be able to see 82 multiplied by 2 divided by 5. Okay, so I'm going to get 32.8 over here. So this is 32.8 plus what I'm actually going to do, I'm going to basically say 3 multiplied by 46.66 divided by 5, and that is nothing but 27.996. Okay, so if I add this plus 32.8 and if I try to subtract it with 60.8, you'll be able to get something this much, right? So I hope the calculation is right, and this will be 0.004 since 60.8 is bigger. So here I'm getting some variance reduction, and here my variance reduction was 0. So I can definitely conclude that variance reduction with respect to the left split, which was basically using that, is less than variance reduction with respect to the right split, which we made it, right? So obviously if I try to compare out of this two, which is the better split, I will definitely select this split. Okay, so this split will basically be selected for solving the decision tree regressor. And we basically use this particular step to find out with respect to, as we go ahead again, we can do further splits and we can probably try to find it out. And similarly, even I have continuous variables, I have to make different splits and then try to find out which is the best split going ahead, right? So variance reduction is a very important property with respect to decision tree, whichever variance reduction. Now when I say left split, this was the left tree, right? Left tree, this tree, right? This tree, again let me mention which tree. So this was the tree, right? Less than or equal to 2. This was the tree that we are actually checking with, less than or equal to 2. And if I talk about the variance reduction, which I got some value, because over here this value that I got was 0, right? This value I got was something like 0.004, right? So obviously here you can see variance reduction on this side is greater, and this split that we made was less than or equal to 2.5. Further we can make any number of splits, so finally you'll be able to see that we will try to find out the variance reduction, and that is how we'll be able to select that which split should be selected when compared to the decision tree classifier where we use function gate. So I hope you have understood this, and again you need to understand one more thing. Finally, let's say if this was my split, okay, let's say if this was my split that was selected, okay, and let's say this was my root node over here. What is there in the root node that I'm getting? Let's say this is my root node, and here I'm getting as 40, 42. So here I'm getting as 40, 42, and here I am probably getting total values 52, 60, and 56. 52, 60, and 56. Let's say I get my new test data, and this test data is basically less than less than or equal to 2.5. So obviously I'm going to go over here. So how I will be able to find out my final output? Let's consider this is my leaf node. Let's consider, I'm saying, okay, after probably all the splits and all. So finally you'll be able to see the output will be the average of both these values. Okay, now in this particular case my output will be 41, and this usually happens in regression. Any number that is greater than 2.5 will come over here, and here we will try to find out the average. 52 plus 50 plus 60 plus 56 divided by 3. So if I probably go and compute the average, it is going to be 52 plus 60 plus 56 divided by 3, right? So once I get this, you'll be able to see that I'm getting 56 as my output. So if it comes over here, the average output is basically the output of the decision tree regressor. Okay, so this is super important to understand. Apart from that, we have understood what exactly is variance reduction and all, and how do I calculate variance reduction with respect to both the different types of splits, right? So yes, this was it. I'll see you all in the next video. Thank you. Hello guys, in this video we are going to implement decision tree practical implementation, and for this I'm going to take a very simple data set, and then we'll try to create a decision tree. We'll also try to plot a decision tree by using all the concepts that we have learned in the theoretical intuition regarding decision tree entropy, Gini coefficient, and again information gain. So let's go ahead and let's see like what data set I'm going to basically use today. So first of all, I will be importing some libraries, import pandas as PD, import matplotlib.pyplot as plt, and then I will also make sure that I will import numpy, probably I'll be requiring it, and percentile matplotlib inline. So I will use all these things as in most of the practical projects that we do. Then what I'm actually going to do is that we will load the iris dataset. Now iris dataset, in order to load it, I will say from sklearn.datasets import load iris. Okay. So here you have a lot of datasets that are available inside this also, inside the sklearn itself. So once I import it, all I will then do is that probably create my iris dataset and just write load iris, right? So once I do this, if I probably go and execute about iris, right now here you'll be able to see I'll be getting some key value pairs like this. Okay, so the first key value pair is nothing about the data. In our data we have specifically 4 input features, 4 independent features, and there will be one more key value pair which will be in the form of target. Target is basically saying what is the output, whether it belongs to the 0 class, first class, or second class. And the target names, if you see, it is nothing but setosa, versicolor, and virginica. So based on these 4 input features, we need to predict what the type of the iris flower is, whether it is setosa, versicolor, and virginica. And if you really want to understand what are these 4 features, then here it is nothing but it is basically showing like sepal length, sepal width, petal length, and petal width, right? So these are some of the features of the input or independent features that we specifically have. And probably there will be also something called as feature names. Let's see whether we'll be able to find out feature names, or if I probably just write iris of description. Okay, there's one key. So here you'll be able to find out all the information. Again, it is not printed properly, but let's see whether I can see that information by just printing it. So here it is how it looks like. It has number of instances as 140, 4 numeric predicted attributes in the class. These are the attribute information: sepal length, sepal width, petal length, and petal width. And the class is nothing but setosa, versicolor, and virginica. And automatically it is basically encoded in the form of if I probably just print my iris target, so iris, if I probably display iris, and this should be the target. Here you'll be able to see that it is already encoded in the form of 0, 1, 2. So that is nothing but these 3 specific classes, that is setosa, versicolor, and virginica. Now I'm just going to take this particular data set, okay, and we'll try to divide that into independent features, and we'll try to apply a decision tree on top of it, and we'll try to solve this classification problem. Okay. Now, the first and foremost thing will be that let us go ahead and create my independent features and dependent features. Now, if I probably take iris of data, okay, so this will basically give me an array. What I can do is that I can convert this into pd.dataframe. Okay. Now, once I take this as pd.dataframe, and if I execute it here, you'll be able to see all my values of my independent feature. Now, along with this, I can also give my column names, and my column name will be nothing but iris dot. Let's see whether I have my column names or not somewhere here in some keys. Okay, I don't have any such keys. So what I can do, I can basically write sepal length over here. I can basically create my manual column over here. So this will be sepal length in centimeters. Then I can probably create sepal width. So this will basically be my sepal width, and it will be petal length and petal width. So 4 columns: petal length and petal width. Okay. So once I execute it, now you'll be able to see my entire data set, right? This entire thing I'll be storing it in my x-axis, which will be my independent feature. So here I will write it as my independent features. Okay. And similarly, y value, I can probably put it as in the form of iris of target, right? So this will be my dependent feature. So this becomes my dependent features, right? Perfect. So these are my x and y. Next, I will be doing something called as train test split. I hope everybody is now familiar with this. So from sklearn.model selection, import train test split, and here I'm basically going to write x train, x test. Okay, this x underscore train, x underscore test, y underscore train, y underscore test, and here I'm basically going to say train test split. Give my x, comma y, comma test size. Let's say my test size is 20%, 0.2, and here I can basically write random state, any random state that you want to do the train test split. Let's say I want to use 10, and I'll execute it. So this is how I've actually created my train test split. Now, in order to apply decision tree, right? First of all, in decision tree you don't require standardization or any kind of normalization. That is not at all required because with the help of decision tree we'll directly apply the algorithm. Now, in order to apply decision tree classifier, first of all I'll be importing from sklearn.tree import decision tree classifier, and then this will basically be my tree classifier, and I can initialize my decision tree classifier. And here you have multiple parameters. Okay, so probably if you press shift tab, you'll be able to see many parameters like criterion, Gini, splitter best, max depth, min sample splits, minimum samples leaf, maximum features, and you can all play with this specific parameter. That will definitely play with the help of hyperparameter tuning. Like what all different features can be selected, we will definitely play with it, and we'll do that hyperparameter tuning with the help of grids or CV. Okay, but right now whatever is the default parameter, we're just going to take that. Okay, so once I execute this, and then I will say tree classifier dot fit on x train, comma y train. Okay. Now, once we do this particular fit, all we have to do is that prepare or create this entire decision tree, how it is basically created, and we'll try to visualize. Okay. So now I'm just going to write visualize the decision tree. Okay. And here I will say from sklearn, I'm going to import something called as tree. Okay. And then I will say plt.figure. I'll just initialize my figure with some fixed size. That is 15, 10, let's say. And then I will say tree.plot underscore tree. And here I'm basically going to use tree model. comma filled is equal to true. Okay, so once I execute this, I'll be getting some error. Tree model is not defined. Okay, sorry, I should write tree classifier. Okay, here you can basically see the entire decision tree classified in a visualization way. You're basically visualizing an entire decision tree, and what all information it is basically saying. Let's understand this. Okay, so first of all, the first over here, the coefficient that is used is Gini coefficient, and here you can see that initially this many number of samples you had in your training data set. Then taking this condition x of 2 feature, whichever feature it is, less than or equal to 2.5, it has made one split. Probably the information gain was high in this case, and the other split is basically made over here. Here you can see that I'm getting a leaf node. Now whenever I get a leaf node, your Gini becomes 0.0. That basically means your Gini is going to range between 0 to 0.5 in every splits. Okay. And that is what we have already learned in our theoretical intuition. In the case of entropy, probably if I use entropy over here, your entropy value will be ranging between 0 to 1. Now here if you see if it is 0.0, that basically means it becomes a pure split. If your Gini value is 0.5, that basically means it is an impure split. So I have to further do the splitting. Here you can see that I've got a pure split, so I don't do the further splitting. Similarly, I do the further splitting over here. Here also you can see I can get the Gini of 0.057. Still, there is some amount of splits that is required. Now I will basically do the further split, and now here you can see this is also a leaf node that I'm getting. This is also a leaf node. This is also a leaf node. Right? Now similarly over here, x of 3, based on this particular condition, I did the further split. Here I got the Gini as this much. Here you can see if I get Gini as 0.59, that basically means it is a impure split. Right? If I get near to 0, it becomes a very good pure split. But again, there is one other category, so we further do the split. Now this becomes a leaf node. Now this kind of split will happen completely from top to bottom. Okay. And now whenever we try to have this kind of scenario, now let me rub this quickly, and I hope you have understood this visualization representation of the entire decision tree, visualized representation. Now one very important thing is that usually when we create this kind of decision tree, right, it leads to something called as overfitting. Why? Because we are basically splitting our decision tree completely to its depth. So how to prevent overfitting? Now preventing overfitting is usually done by two ways. One is post pruning, and the second one is something called as pre pruning. Right? In post pruning, what we do is that we try to construct the decision tree completely to its end, and after that we see at this point of time I can definitely say that further splits were not required. Why? Because you can see maximum number of categories that I get over here is for the second category. Here maximum number I get is for third category. So why I needed to basically split it again, right? Because the small number will not play a very important role, right? So whenever at this particular side, whenever my decision tree will probably come, I will definitely say that this belongs to the second category. If it probably comes it over here, I'll definitely say that it belongs to the third category. So this technique, after constructing the entire decision tree and then pruning it, we basically say it as post pruning. In pre pruning, we play with various parameters like max depth, which coefficient we need to use, whether Gini or entropy. Then we can basically say how many number of max features we can create. So this is basically we'll try to hyperparameter unit with the help of pre pruning, right? We'll hyperparameter unit, right? Now in this video we'll try to cover post pruning. Obviously in this in the upcoming video we'll see pre pruning. Okay. Now in post pruning what we have done is that, see, in post pruning we have understood till max depth 2, right? After max depth 2, after this particular depth, we don't require further splits. So we can stop it over here. How? We can set this max depth to 2. Okay, because we know that further split is not at all required. Okay, now let's do this and let's see how we can basically do this. Now whenever we are creating this decision tree, all we have to do is that I'll press shift tab over here, and here you'll be able to see one parameter which is called as max depth. Now if I probably set up this max depth to 2, then what will happen? Here you'll be able to see I'll be able to get till second depth, and now this will be more than sufficient to do the further prediction. Right? Now further prediction, how I'll do? I will take up this model, which is the model that we basically have over here, tree classify, and I'll do the prediction. See, tree classify dot predict. Okay, on my x train. Right? Now once I do this, sorry, on my x test. Once I do this, I will basically get my y underscore pred. Okay, and then what I can do is that I can say from sklearn dot we will probably consider metrics. I'm going to import confusion metrics and classification report. Okay, once I execute it, here you'll be able to see CM with confusion metrics. Here I can basically write y underscore test, comma y underscore pred, and then I will print CM. Okay, and then I will probably also write classification report where I will be printing classification report on y underscore test, comma y underscore pred. Okay. So once I execute this, here you'll be able to see I'll be getting somewhere around 93% accuracy with respect to precision and recall. Only 2 points have got misclassified over here, right? Remaining all the diagonal elements are getting correctly classified. So at an average, I'll be getting between 93 to 95, right? Now you may be considering whether we should do post pruning or pre pruning. Post pruning is always good for smaller data set, guys, because if you have a huge data set, right, we really need to construct the entire decision tree, so it will take more time. So post pruning, just try to do it for smaller data set, but usually the best way is that we have to do pre pruning because there are a lot of parameters in decision tree, like criterion, splitter, max depth, minimum sample split, minimum sample leaf, right? Max feature, random feature, max leaf node. We have to play with all these parameters, and then we will basically play with this with the help of hyperparameter tuning or randomized or CB, and then we can select the best parameters applied to decision tree. And that technique we'll try to use it in pre-pruning. Right now, here we are focused more on decision tree classifier and post pruning. So I hope you have got an idea about how post pruning and decision tree classifier works, and we have also seen that how the visualization basically looks. Okay. Now by default, I'm just going to make sure that I don't put any max depth and probably help you to understand or help you to initialize the max depth over here. Okay. And obviously there are other parameters which you can also see. Now let's go and see with respect to this particular accuracy also. So here you can see that one more wrong point has got reduced. Right. Just imagine, because even though we have completely done this split till that leaf node, all the leaf nodes, what else we could do? Only one point we could accurately predict better than the previous one, which was only for max depth 2. So yes, this was it. I will see you all in the next video with the pre-pruning technique, and we'll also do hyperparameter tuning. Hello guys, in this video, we are going to discuss about decision tree classifier, and here we are specifically going to discuss about pre-pruning and hyperparameter tuning, right? So both of these things we are going to discuss over here. I'm just going to make sure that I update this and write hyperparameter tuning, okay? So we are going to do both of them. Now whenever I said about pre-pruning, in our previous session we have already seen we have created decision tree completely to step, and after that we can definitely apply post-pruning, but again post-pruning is just, it will just be useful only for smaller data. For bigger data we cannot see the complete decision tree, right? Now in order to do decision tree pruning, we have to really play with a lot of parameters. So if I probably go and write sklearn decision tree classifier, and if I go inside my scikit-learn, here you'll be able to see a lot different parameters are there, like criterion, splitter, max depth, min sample leaf. Criterion can have Gini, entropy, log loss. Splitter can have best, random. Max depth can have different values, and similarly minimum simple split is there, minimum weight fraction, maximum features, it can have anything, right? And based on this particular data set, right, these features may have different values. So we really need to perform some kind of hyperparameter tuning over here. So the first thing what I will do is that I will just try to take all the specific parameters. Already I have my X-train and my train data set. So let's play with the specific parameters. So here I'm just going to define my params, and this I will define in the form of key value pairs. Okay. Now the first thing is that I will play with criterion. Okay. So let's go and select the specific criterion over here, and I'm just going to copy and paste it over here. And obviously I will write criterion colon, and this will be Gini. It can be entropy, it can be log loss. So this is the first feature that I want to play, and probably I've shown you how to do hyperparameter tuning using grid search, right? And always make sure that you give this in the form of list, because if you give this in the form of list, then only you will be able to experiment with different combinations. Okay. Then second one is something called as splitter. Splitter can be taken as best or random. So I'm just going to use over here as splitter. This will be colon, and here I'm basically having best, comma, random, right? So both the splitters will be using over here. And then after splitter, you can also try with some more, like max depth is also there. Here you can see max depth. So max depth also we can specifically try with. And here also I will be using different depths, like 1, 2, 3, 4, 5. I know the data set is very small, the data set, and then we'll definitely try to play with this particular parameters. Okay. And then after this, I will probably play with some more parameters. Let's say which all parameters can be used. I can also use max features, and I have all three options. So let me copy and paste over here. Okay. Max number of features. This will be an integer, or we can also assign these values like auto, square root, and log 2. Right, so these are my combination of the parameters that I really want to write out. Okay, and here are my params. Okay, so let's see, criterion is not defined. Name criterion. Okay, I have to give this in the form of keys also, I guess. Otherwise, it will basically key value pairs. Otherwise, it will just treat it as a variable. So definitely, I'm not going to edit this if there is a mistake, so that you'll also come to know what things we are actually doing. Okay, so here it is, here it is, here it is. Okay, perfect. So now if I probably go and see my param, these are all the parameters that I'm going to play with. Now the next step is very much simple. I'll say from sklearn dot model selection, I'm going to import grid search CV, or you can also use randomized search CV. It is up to you. And let me just define a tree model. This will be like with the default parameters over here. I'm specifically defining. And now I will just say grid is equal to grid search CV. Okay. And let's say that I can basically use this tree model, which I have to give as my estimator. The second parameter that you'll be seeing is something called as param grid, and this will get assigned to param. Okay. Then I will also have cross validation. Let's say I'm using cross validation equal to 5, and my accuracy will be equal to, okay, what accuracy? It is scoring parameter. Scoring parameter will be equal to accuracy. And probably we have done all these things, guys, again and again. So I'm just making it quick. Okay. So once we do this, and finally we do just grid.fit on X train, Y train, we are going to get some kind of errors or warnings, not errors, warnings. So remove, or if you probably search for import warnings, right? So this is how you can remove the warnings. If any warnings is basically coming while you're training the model. So I'm just going to import it over here, import warnings, and then I'm going to say warnings.filter warnings. Warnings.filter warnings ignore. Okay. So if you do this, automatically all the warnings will go off. And now I will start my training process. And yes, the training process has been started and it has got completed since the data set is very small. Now all I have to do is that go ahead and see on grid.best params. And if I probably, sorry, this will be in the form of dictionary. The best params that are selected is Gini, max depth is 5, max feature is square root, splitter is random. Okay. So these are all the best parameters that you've got. And probably if I go and see my grid.best score, also you'll be able to see some percentage, that is 95%. Now apart from that, if you really want to go ahead and probably calculate all the metrics like confusion metrics and all, you can definitely do that. So for that, all you have to do is that, right, y underscore pred is equal to grid.predict. And here I just want to give x underscore test. Okay. So here I will basically get my y underscore pred, right? And let's see my accuracy. So for getting the accuracy, all I have to do, I'll just copy and paste this entire thing, confusion metrics and all, and we will be able to see some good things. So here you can see with respect to my test data, I'm getting 4 wrong outputs, remaining all are correct. At an average, I'm getting somewhere around 95 to 96%. And if you also see some score, I will also import one more parameter over here from sklearn.metrics, import accuracy score, and this score will be using accuracy score on my y underscore test, comma y underscore pred. Okay. So this is how you basically do pruning, post pruning. You play with different parameters. There are still many parameters which you can try, and for the test data it is giving 86%. It is making sure that by playing with this particular parameter will not lead to overfitting, and you try to select the best parameter that is suitable with respect to a data set. Obviously this is a small data set, so you'll not be able to see it, but later on when we do a lot of end-to-end projects, then you'll be seeing that how we can use with this entire parameters in a different way, and all this combination of parameters will actually help you get a better accuracy. So yes, in this video I have actually shown you how to train a decision tree classifier, do the pre-pruning, and this hyperparameter tuning and pre-pruning are one and the same in this case, because here we are able to decide what will be the match depth based on the various combination that we have. Okay. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, in this video we are going to implement a project which is called as diabetes prediction using decision tree regressor. Again, in the decision tree classifier we saw that how we can apply decision tree algorithm. Along with that we also see that how we can perform hyperparameter tuning. So similarly with respect to decision tree regressor also we will be seeing how we can apply this specific model and also do hyperparameter tuning. Now first of all, when we start it, right, we really need to get the data set. So from where we can get the data set. Again in sklearn there is a important library or function which is called as load libraries, and from that we'll be able to get this diabetes data set. So I will go and execute it by importing the library from sklearn.datasets import load underscore diabetes. So once I execute it here, in order to load the data set, I will just need to call this load diabetes or initialize this, and automatically I will be able to see the data set. So let's go and see the data set. The first thing once you see the data set over here is that, right, if I see this data set, it has 3 key value pairs. One is the data. So over here you'll be able to see that how many number of features will be there. Right, these are all my independent feature. The next key is basically about the target. This target is my dependent feature. Okay, so definitely this is a regression kind of problem. We'll anyhow understand about what all features are basically present. Now let's go ahead and see in the description. In description, if I probably take this key and print it over here, let's say if I write print data set of description, I'm just calling this key. Here you can basically see. Here you can see that the number of instances, that basically the number of data points is 442. The 10 columns that you see, the data points that you see over here, right? All these particular data points belongs to this 10 columns. So what are the columns? The columns are age, sex, BMI, BP, S1, S2, S3, S4, S5, S6 are different serum of blood. Okay, so different blood samples in short. are basically represented by this all features S1, S2, S3, S4, S5, S6. So these are all my dependent features, sorry, independent features. Now what about my dependent features? So if you see over here, if I probably print this, right? If I probably print this, here you'll be able to see these are all my independent features, and my dependent feature will be somewhere here itself. So the target column 11 is a quantitative measure of disease progression 1 year after baseline. So after 1 year, what is the disease progression? It is just given that. Okay. So that specific information is basically given in our target variable. Okay. So what we're going to do now is that first of all, we create a data frame for our data set with respect to the target and the independent feature. So all I will do over here, I'll say pt.dataframe. I'll give my dataset.data because this is basically having my independent feature, and I'll give all my column names with age, sex, BMI, BP, S1, S2, S3, S4, S5, S6. This will nothing be. This will be basically be all my independent features. So once I execute this and probably execute df underscore diabetes dot head, you'll be able to see this is how my output look like, right? So this is my entire dataset that you'll be able to see. Okay. Then after this, I will try to split my dataset based on independent and dependent features. Okay. Now here you can see once I split this particular data set based on independent feature, so X will be my independent feature, which will be entirely this DF underscore diabetes, and Y I can basically write it as data set of target. Okay. So once I execute this, I will be able to get my independent feature. This is pretty much simple, and this we have performed any number of times. After that, I will perform train test split. In order to perform train test split, all you have to do is that import from sklearn.model selection, import train test split. I'll use a train test split with X, Y, test size is 0.3, and random state as 10. Okay. So let me go ahead and execute this, and this will basically be my xtrain.head. And I can also check my correlation. So in order to check the correlation, by default, we will be checking Pearson correlation. All I have to do is that I just need to write X underscore train.correlation. So once I execute it, here you'll be able to see the entire correlation with respect to all the independent features. So this is just to show you that how one feature is related to the other feature. Okay. Then with the help of heat map also I can see the correlation. All I have to do is that set up a plot's figure size and then just use sns.heatmap x underscore train.correlation with annotation is equal to true. And once I execute this, here you will be able to see. First of all, let me import matplotlib also. So import matplotlib.pyplot as plt. So once I execute this, you'll be able to see my entire heat map. Okay. So till here everything is perfect. Now the next step is that I'll just try to apply my decision tree regressor. So from sklearn.tree, I'll be importing decision tree regressor. Then regressor will be nothing but decision tree regressor where I'm initializing this. Again, I'll just do regressor.fit on xtrain and ytrain. Okay. So once I execute this, my decision tree will be ready. And but this will not be sufficient. If I probably do the prediction also, I may not get that, or it may also lead to overfitting because I'm trying to create a decision tree completely to step. I'm splitting it completely to step. So in order to prevent this, what we'll do, we'll perform hyperparameter tuning. Now hyperparameter tuning, what I'm actually going to do is that just open sklearn decision tree regressor. Okay. And probably go and see over here. Here you can see that I have so many features. I have criterion, I have splitter, I have match depth, like how we had for decision tree classifier. Now over here you can see in decision tree regressor, I have different criterion like squared error, Friedman MSE, absolute error, Poisson. All these are my features, right? Different criterion that I can use. So I will probably do a hyperparameter tuning with respect to all this criterion. I've already discussed about MSE, mean squared error, and squared error, right? How decision tree regressor actually works based on this. So anyhow, we will try to perform on all this, which will be the best feature based on our data set. Okay. Then similarly, we can use splitter also as our hyperparameter and select all the possible options. Max depth also I'll try to select, and along with that I'll also try to select max features. Okay. So here you can basically see that I've selected criterion, all the possible options, splitter, best and random, match depth I've selected 1, 2, 3, 4, 5, 6, 10, 15, 20, 25. Okay. And max feature, auto square root, and log 2. These are the possible options. So this will all be my key value pairs. So if I probably see my parents option, this is my key value pairs. And with all these things, I will be performing grid search CV. Now for the grid search CV, all I have to do is that just import from sklearn.model selection, grid search CV. Once I do that, here you can see regressor is equal to decision tree regressor. I'll try to execute it. After this, I will try to create my grid search CV along with regressor, parent grid, cross validation, and the scoring parameter. In this, the scoring parameter that I'm using is negative mean square error. So if you really want to see with respect to regression, what are the different scoring parameters, just go and search for sklearn scoring. Okay. Now if you go over here you'll be able to see for classification you have this many number of scoring parameters. For regression, you have this many number of scoring parameters. Out of this, I've used negative mean absolute error. You can also use negative mean square error or root mean square error. It is up to you. Okay. So here I've basically taken negative mean square error. All I'll do, I will just go and execute this, and then I will just fit it with train and xtrain and ytrain. I've imported these two libraries because I was getting some amount of warnings. So I want to remove those warnings also. So now let's go ahead and do the fit. Once I do the fit, you'll be able to see the fit will get completed. And if I probably go and hit grid.best underscore params, then here you can see what all parameters that got selected. With respect to criterion, Friedman underscore MSE has got selected, match depth 4 has got selected, max feature log 2 has got selected, splitter as random has got selected. Okay, so this is quite amazing. We have got some amazing outputs. Then we do the prediction. So here I will basically do the predictions. And then with the help of metrics, I can basically calculate my R2 score, mean absolute error, and mean square error. And this is what we basically use for regression. So finally, this is what I'm actually getting with respect to mean absolute error, mean square error. Now, all you can also do is that if you really want to see with respect to this all features, how your decision tree will look, just copy this entire feature, create your model. Okay, once again, put all this criterion, Friedman underscore MSE, match depth 4, max feature log, splitter as best, but here I'll use it as random. Okay. Now once we do this, and once I execute and fit on xtrain and ytrain, then visualize the decision tree by using this tree.plot underscore tree, where I'm using the selected model with field is equal to true. Now here you'll be able to see this is how my decision tree will look like, right? And since there's so many features into this, obviously your decision tree will look very small, right? And if you also want to probably zoom in and see, you can basically see like this. Okay, it is not that clear, but here you can see that one idea like how the decision tree split has basically happened. Okay, so yes, this was about decision tree regressor. At the end of the day, you can see that I was able to get this the visualization. And again, we did a good amazing project with diabetes prediction dataset, and this particular dataset, more information you can find out in this specific link also, right? This link. If you could probably click on this link, you'll be able to get all this information. What is this dataset all about? You have features like age, sex, BMI, BP, S1, S2, S3, S4, S5, S6, and Y is your dependent feature. Okay, so I hope you have understood this particular project. Yes, I will see you all in the next video where we'll be learning more about different projects using different algorithms. In this video, we are going to discuss about something called as ensemble techniques. And in this ensemble techniques, we specifically have two types, that is bagging and boosting. So at the end of the video, you will be able to understand what exactly is bagging, and we'll also try to understand what are algorithms we are going to learn inside bagging. And similarly, we'll also try to understand what exactly is boosting. Now, first of all, let's go ahead and understand what ensemble techniques are. Okay. Now, till now, you have learned about so many machine learning algorithms. but we have never seen wherein we combine multiple machine learning algorithms for doing some kind of predictions. Okay, so ensemble techniques actually helps us to combine multiple algorithms together, probably train that specific kind of model, and then with respect to that, we get some kind of output. When we are combining multiple machine learning models, there are chances that we definitely get good amount of accuracy. So in most of the platforms that you will probably be seeing or you may have heard about, like Kaggle, there are hackathons, competitions in Kaggle, and different hackathons, right? And even in different hackathons, many people, while they're solving the machine learning problem statement, they use this kind of ensemble techniques, specifically bagging and boosting techniques. Okay, and with respect to any kind of problem statement, ensemble techniques like bagging and boosting gives you very good accuracy. So now let's go ahead and understand first of all what exactly is bagging, okay, and what we exactly do in bagging. Okay, now some of the algorithms that we will probably learn in bagging is something called as random forest. Okay, random forest. Now here we'll discuss about random forest algorithm in the later stages, but let's understand the basic, what is the idea behind bagging. Okay, idea behind bagging, and then we will probably go and learn about what is the idea behind boosting. So in bagging, what we do is that, suppose let's say we have a specific data set. Okay, let's say that we have a data set over here, and data set can be of any size, any number of data points, and it probably has some amount of features and some amount of data points itself. So let's say this is my data set. Okay, so over here this is my entire data set. Now for this particular data set, let's say that this is my training data set altogether. Okay, so training data set. Now in bagging technique, what we do is that we have multiple base learners. Okay, we have multiple base learners. Like this may be my separate base learner, base learner. When I say base learners, these are specifically different machine learning algorithm, or it can be same machine learning algorithm. Let's say that this is my decision tree. Okay, this is my decision tree. And let's say this is my logistical regression for a classification problem. Suppose if we consider for a classification or for a regression problem. So over here, what I'm saying is that we have multiple base learners like this. And these base learners are basically our machine learning algorithms. And we can have many number of base learners like this. Okay. Now what happens in bagging is that we give some sample of data set to our model 1. Let's say this is my model 1, this is my model 2, this is my model 3. Like this, I can have any number of models. Let's say this is my model n. Okay. N. Now what we do in bagging is that we use base learners like this. It can be same algorithm or it can also be a different algorithms. Okay. What we do, we give a sample of data set to model 1 and another sample of data set to model 2. Similarly, another sample of data set to model 3 and another sample of data set to model n. Finally, when we give this particular sample of data set, this model gets trained with respect to this specific data set. Similarly, this particular model will get trained with the other sample of data set. Similarly, model 3 and model n will also be getting trained like that. Okay. Let's consider this is my another model like XGBoost. Okay. Not XGBoost, but XGBoost is already a boosting algorithm. Let's say this is my naive bias. Okay. So these are algorithms which I have already discussed. I'm just writing it over here. Now after this, once the model is trained with different sample of data set, then what happens is that when we give our new test data for the prediction, let's say if you're trying to solve a classification problem, let's say this is a binary classification problem that we're trying to solve. Okay. Binary classification problem. So what happens is that when we pass this specific new test data, then this new test data will go over here, and obviously decision tree will do some kind of predictions. Let's say this is giving me 0, this is giving me 1, this is giving me 0, and this model and whatever algorithm we are using, this may be giving you this. Let's say that this is also giving somewhere around 0. Okay, 0. Now overall, if you really want to find out the final output in this specific way, then what we use specifically is we use something called as majority voting classifier in the case of regression problem statement. That basically means they will go and see that each and every model, which we are specifically saying it as base learners, what output they are giving. Like maximum number of models are actually giving the output as 0. So our final output based on majority voting classifier will be 0. Okay. This is the idea behind bagging. Okay. Here we have some specific base learners. We pass some amount of data to machine learning, different machine learning models. Let it be a classification problem. Now in the case of regression problem, like if we have a regression problem statement, okay. Now in this particular case, what we do is that we specifically, like in the regression case, this output will be a continuous value, right? So the final output will be the average of all outputs. Average of all outputs. So this exactly is basically how a regression problem basically works in the case of bagging techniques. So some of the key points, let me repeat over here. You'll have a data set, and what you'll do is that you can take many number of base learners. Like how many number of base learners you want, you can basically take up. Okay, there are options. By default, it takes up 100 base learners. If one of the algorithm, if I talk about like random forest, then what we do, we take sample of data set from here. Let's say I'm giving D dash over here, D double dash over here, D triple dash over here, and D4 dash over here. So these are different sample of data set. And when this model gets trained, then it will start taking the new data and make the prediction. Final output will basically be the majority voting classifier in the case of binary classification or multi-class classification. At that time also it will be considered majority voting. So who's voting what maximum amount? Like if this is voting maximum, models are voting 0, then it is going to consider 0. Otherwise it is going to consider 1. In the case of regression, whatever output I'm getting continuously, we are just going to find out the average, and that is how the output is coming up. Okay. Now this was the idea behind bagging. Okay. Now let's go ahead and understand one important thing about bagging. All these base learners are getting trained parallelly. You have to understand this important point. All these base learners are getting trained parallelly. Okay, not sequentially, parallelly. So if I now talk about boosting, let's go ahead and understand about boosting. And in case of boosting, there are different algorithms that we are going to learn. First of all, let's say we're going to start with something called as gradient boost. Okay. Then we are going to start with XGBoost. Not gradient boost. First of all, we'll start with something called as ADA boost. Okay. So we are going to start with something called as ADA boost algorithm. And this bagging and boosting algorithms are used for solving both classification and regression problem. Okay. ADA boost is there. Then I have something called as XGBoost. And before XGBoost, we can also use something called as gradient boosting. And then my third is basically extreme gradient boost. Okay. Extreme gradient boost. I will probably be teaching you all these things as we go ahead. Okay. Extreme gradient boost. So this is also called as XGBoost. So these all algorithms we'll try to see in much more depth and detail. We'll try to understand how does this basically work. Now let's understand the fundamental idea behind boosting. Okay. So how does boosting algorithm actually work? Idea behind boosting. How we are going to combine multiple models in the case of boosting. In boosting, like in bagging, we had base learners, right? In boosting, we basically say that we have weak learners. Okay. So let's say this is my one model M1. It can be anything. And then I will be having my another model M2. Or let me just make one small change over here. Let's say that this is my data set. Because I missed the data set over here. So let's say this is my entire data set. Okay. And let's say I have separate models. So I have all the weak learners. And let's say this has base learners, but I'll say weak learners. So let's say this is my model M1. This is my model M2. This is my model M3. And it can be any number of models, right? All these models are connected sequentially. Okay. Sequentially. So this is my M1, this is my M1, and this is my M2. Okay. So I can have any number of models. All models are basically called as weak learners. Okay. weak learners. These are also called as weak learners. Similarly, in this case, this is also a weak learner. And they are connected sequentially. Okay, understand? These are connected sequentially. Sequentially. Okay, and similarly, this is also a weak learner. Now, the idea behind the boosting technique is that we combine all the weak learner, and finally, when I combine this all sequentially, we actually get something as a strong learner. Okay, strong learner. Now, see in this particular case how it actually works. In boosting, first of all, I will give out my entire data set to model 1. Okay. Now my model 1 will train and it will give some kind of accuracy, and it will obviously be able to not, like let's say for some of the records it has not predicted correctly. Let's say there are around 10 to 15 records that are not predicted correctly over here. Then what model 1 will do is that it will pass those records that are wrong, that are incorrectly predicted, along with some more records from this data set to model M2. Okay. And similarly, model M2, it will train from that specific records, and it will also not be able to predict some wrong records. It will obviously predict some wrong records. So it is going to pass that wrong records to M3 along with some more records from this data set. Okay. And this process will keep on continuing sequentially with some n number of models. Now what happens is that whenever I try to give a new test data, okay, then each and every model will have its own strength, and based on that it will be able to give the predictions, right? Once it is being able to give the predictions, overall when we combine all the predictions, again the same thing, we can actually include majority voting classifier, or we can also get with respect to, if you try to find out average, you'll be able to get the regression problem statement. So in short, in boosting, we are combining multiple weak learners together to form a strong learner. Just in a basic example, if I really want to give, let's say there's a problem statement that involves 4 to 5 different domains. Okay, that domain can be physics, chemistry, it can include geography and all. Now just understand, this weak learner are like the people. Suppose this model is basically very good at geography, so he will be able to give, he or she will be able to give some amount of information from this particular problem statement, some solution for this problem statement. Then when we go to the model 2, then it will be able to give some solution from this particular problem statement. Let's say model 2 is an expert in physics. Similarly, this is an expert in chemistry domain. This is an expert in some other domain. So when we combine all this little knowledge, finally you'll be able to see that we are getting a strong learner and we'll be able to get the prediction. Right? Similarly, in the case of bagging, here what you see that each and every model is an expert with respect to its own specific subset of data. Right? So this model, they are own expert in their own specific subset of data. So definitely they will also be able to give some good solution with respect to any kind of problem statement that we have. Specifically when I'm talking about regression and classification. So I hope you got an idea about what is the basic difference between bagging and boosting. Now in my next video we'll start with random forest. So random forest is one bagging technique which we are going to learn about this particular algorithm, and we'll try to understand how regression and classification is basically solved using random forest. Okay, classification. We'll try to understand the detailed implementation about this and the mathematical intuition, right? So, and after that, we'll continue the boosting part. So, yes, I will see you all in the next video. This video I've spoken about what is the differences between bagging and boosting, and these are specifically ensemble techniques. One of the example of bagging techniques is random forest classification and regression machine learning algorithm. So let's go ahead and let's try to see how this algorithm actually works. Usually, let's consider that I have a specific data set. Let's say that this data set is there, and the size of this data set is, I want to mention the size of the data set as D, okay, a small d. So this is basically small d. So this is the size of the data set. Similarly, if I consider what is the size of how many features I have, let's say that I have total m number of features. Okay, I'm just giving some notation so there may be like f1, f2, f3, f4 like this up to fm features. Okay, some n number of features, and obviously this is my entire data set. Okay, now in random forest, as it also uses the approach of bagging only, but over here the base learners that you actually have, all the models of the base learners are decision trees. Okay, so this is my decision tree 1. Let's say this is my decision tree 2. Okay, let me draw it again much more better, and this is my decision tree 2. This is my decision tree 3. Okay, decision tree 3. Similarly, I have a lot of decision trees. So over here, your base learners are specifically decision trees, and it can have any number of decision tree. Okay, now this is fine. Okay, fine. My base learners are decision trees. Now let's see how this entire, and obviously you know how to create decision trees, right? We have seen techniques related to regression classification. In classification, we have seen entropy, gain impurity, information gain, and how we construct the entire decision tree. Similarly, in regression, we use something called as mean square error. Now what happens is that with respect to this particular data set, and obviously in bagging technique, I told you that we need to give a sample of data set. So here we are going to do something called as row sampling. Row sampling. So I'm basically going to do some row sampling over here. So let me write it down properly over here. So we are going to do some row sampling. Row sampling from this specific data set. Let's say from this particular data set, I'm going to pick up some rows. Along with row sampling, I'm also going to do something called as feature sampling. Okay, feature sampling. So here in short form, I'm just trying to write it as RS plus FS. Okay, so we are going to do some amount of row sampling. Row sampling basically means we're going to pick some amount of rows from this data set, not all the data set, but some amount of rows. Let's mention this is like D dash, and obviously if I say D dash, that basically means D dash is less than D, right? D is the total number of data points, right? And D dash, I'm just picking up some of the rows. And similarly, feature sampling. Let's say that in this, I'm going to pick up F1, F2, F4, and probably give it to this specific model, that is decision tree 1, which is my model 1, and it will get trained over here, right? Now in the second case, what will happen is that again, we will take up some more data set and give it to our decision tree 2. So here again, we are going to do row sampling with replacement. Okay, please make sure that you remember this word, replacement. Why we are doing replacement? Because some of the rows may get repeated from here, but we are also replacing some more rows, right? So row sampling we are doing, but we are also replacing it so that all the rows should not be same when compared to the model 1 rows that are training data set that we are given, right? So here we'll do rows sampling with replacement. Similarly, here also we'll do feature sampling with replacement. So in this particular case, I may give some other features, F1, F2, F5, F6. Yeah, some of the rows and features may get repeated, but that is fine. Okay, but majority of the rows will get replaced. Majority of the features will get replaced. The same thing we are going to do for this particular data set also. So here also we are going to do row sampling plus feature sampling. Here also we are basically going to do row sampling plus feature sampling. Now all these decision trees. One important thing is that in random forest we use only decision trees, right? Now all these decision trees will get trained with respect to this all training data set. Okay. Now whenever I give my new test data, whenever I try to give my new test data, let's say this is my new test data. Now, whenever I give my new test data, what will happen is that, first of all, let's say decision tree 1, in the case of classification, it gives my output as 0. This also gives my output as 0. This also gives my output as 0. And final tree basically gives my output as 1. Now, in this particular scenario, what we are going to do is that we are going to take the majority voting classifier in classification. Okay. So here I'm going to basically write in classification, you'll be seeing that the final output will basically be the majority voting classifier. Right? So here, with respect to classification, we do this. Similarly, with respect to regression, if this is a regression problem statement, then the output will be continuous. So in regression, we basically calculate the average of all the model output. Okay. So again, I'm going to write this two specific conditions over here. So with respect to classification, majority voting classifier will actually happen. Majority voting classifier will happen. In case of regression, we are going to just find out the output. So in regression, output of the models, sorry, average output of the models. Here, I'm just going to write average output of the models, right? So this is how we are going to get the output. Now this is fine, very simple, row sampling, feature sampling, okay, all the models are getting trained. There was one very important interview question that was asked to some of my subscribers, when they went for the interview, and that is that why should we use random forest if decision instead of decision tree, okay, instead of decision tree. Now understand why I'm specifically asking this question. Because obviously to create this many trees and probably train it, right, the time complexity is usually high, right? In this particular case, what is the major disadvantage that I feel? The time complexity to train this model will obviously be high, but accuracy, it will be better because I have so many base learners and so many experts over here, right? So decision tree 1 is a separate expert, decision tree 2 is a separate expert. So maximum number of people what they are saying, or maximum number of models what they are saying, we are going with respect to that specific output. But to train this model, time complexity will be huge, okay? Now the question was, why should we use random forest instead of decision tree? So let me go ahead and write about decision tree. If we try to create a decision tree by its default parameter, then we know that it leads to something called as overfitting. Overfitting basically means the training accuracy is high and the test accuracy is low, because we try to divide, or we try to split our entire decision tree, okay, till it's completed. So our, like, by default it is going to do overfitting if we don't do let's say if we don't do post pruning or pre pruning, right? So there are high chances that it may overfit, right? Now whenever I am actually overfitting, I have in the case of when the training accuracy is high, I basically have low bias, and in the case of when the test accuracy is low, I basically have high variance, right? So this high variance, but if I talk about a generalized model, right, a suitable model, if I talk about a generalized model, this model should basically have low bias and low variance. Now our main aim is that this low bias should be low bias, okay, and we will try to convert this high variance to low variance with the help of random forest, okay? So with the help of random forest, we are going to do this. Now how it is going to happen? Just think about it. How it is going to happen? Since we have multiple decision trees, okay? Since it has multiple decision trees, and one more very important point that you can note over here is that for each and every decision tree, I'm giving a separate set of records, right? Yes, some of the records, some of the rows may get repeated, some of the features may get repeated, but we are giving some amount of data set to M1, M2. Similarly, I'm giving some data set to M2, M3, Mn, right? All these particular models, right? So these models are having some amount of information with respect to different sample of data set. So obviously, this with respect to the new test data, we want our test accuracy will not go down, but instead it will go up now. Because why? Because now we all have separate models who are expert in something else. Now let me say that let's bring some 200 new records to this data set. Let's say I'm just going to bring this 200 new records and I'm just going to add to the data set. Now, will my previous trained model get impacted by this 200 new records? I'm just saying you as an example. The answer is no. Why? Because if I really want to train this 200 new records, let's say, it will get divided between all these models, and just sample of data will get here and there, right? And if we also try to predict those, right, since majority voting will always be working in the case of classification, and in the case of regression, we're going to continue with respect to average, so it won't have that much impact, even though we add this new set of records, because it is going to get splitted among all the records, so none of the model will get much impacted by that, right? So that is the reason, with the help of random forest, since we have many base learners, this high variance automatically will become low variance, because our now training test accuracy will increase, because we have many base learners that are trained on separate sample of data, right, by using this row sampling and feature sampling concept. Okay, so I hope you have understood about training random forest classification and regression. Internally, it uses decision tree so that it becomes very much easy, right? So now in this decision tree, we can set up different. This is the entire separate model. This is the entire separate model, because here we are also changing different records over here, right? So I hope you have understood this. And yes, in the upcoming videos, we're also going to see about boosting techniques and all. So yes, I'll see you on the next video. Thank you. Hello guys. So we are going to implement a random forest classification algorithm implementation, and for this we are going to take up a problem statement. Let's understand the problem statement in this specific video. So the problem statement is about holiday package prediction. The problem statement is tripsandtravel.com company wants to enable and establish a viable business model to expand the customer base. One of the ways to expand the customer base is to introduce a new offering of packages. Currently there are 5 types of packages, that is basic, standard, deluxe, super deluxe, king. Looking at the data of the last year, we observed 18% of the customer purchased the package. However, the marketing cost was quite high because the customer was contacted at random without looking at the available information. The company is now planning to launch a new product, wellness tourism package. Now, wellness tourism is defined as travel that allows the traveler to maintain, enhance or kickstart a healthy lifestyle and support or increase one's sense of well-being. However, this time company wants to harness the available data of existing and potential customers to the marketing expenditure more efficient. Okay. So here, let me just read the dataset. I've already downloaded the dataset. The dataset is basically present in this particular link. It has 4,000 calculated rows and there are 20 columns. So to begin with, what we're going to do is that we're just going to import all the necessary libraries, that is pandas, numpy, matplotlib, seaborn, plotly express, warnings. Now here, I'm also going to introduce you to some new libraries and show you. Now, once I execute this, and probably if I go and read this dataset, which is the CSV file, which you'll be able to find in the same folder location or in the resource section, here you'll be able to see that you have features like customer ID, product taken, age, type of contact, city type, duration of pitch, occupation, gender, number of person visiting, number of follow-ups, product pitch, preferred property star, marital status, and many more, right? Now, what you have to basically do based on the problem statement is that they are coming up with a new program which is called as wellness tourism. Now, they really need to understand whether, based on the data that is available of the customer, they need to predict whether they're going to take this specific product or not. And the information they have are all this kind of information that are basically present. Okay. Now, this is the entire problem statement. In the next video, we will start solving it with respect to feature engineering and all, EDA, simple EDA and all, and we'll try to see that how we can train a model efficiently. Until now, whatever models we may have discussed, like logistic regression, or decision tree regression, classification, right, which is used for classification problems. We'll also see that can we use this along with the other models, because it is always a good practice that you really need to try multiple models and then select the best model based on the performance metrics. So we'll decide that and we'll see that which model is the best. Okay. So this was about the problem statement. Now in the next video, we will start discussing about data cleaning, that is how to handle missing values and all. So let's go to the next video. Thank you. Hello guys, now welcome to the feature engineering section of this specific project. We have already imported the dataset and this is how my dataset looks like, okay? And with respect to any dataset, the first thing is that you really need to clean this data. Now in this step, what all things we are going to do? We're going to basically handle missing values, we're going to handle duplicates, check data type and understand the dataset, okay? So first of all, so whenever you really want to check the missing values, all you have to do basically is df.isNull.sum, right? So once you do this, you will be able to see whether there are any null values or not. And obviously there are null values and we'll try to handle it. So here you can see age, there are 226 null values, all this information are regarding every feature which are having basically null values. This is perfectly fine. Now here you'll also be able to see that there are a lot of category features like type of contract, occupation, gender, and then you have product pitch, then you have marital status, then you have designation. So there are a lot of category features. Now with respect to each and every category features, let's go and find out whether it is balanced, imbalanced, or whether there is any spelling, because in gender we basically say male or female, right? Suppose if it is writing spelling mistake of female, right, you'll be able to see the data will not look properly, like it will just show that okay, it has probably 3 categories. And this I already checked in the data set, there was that problem. Now you'll also be able to understand the problem. So here if I basically write df of gender.value constant, here you can see female and the spelling mistake is there. Obviously I could have combined this with this. So that is the reason you really need to check the data set very much properly, okay? Similarly, if I probably go ahead with respect to marital status, here also you can see married, divorced, single and unmarried. I think both this can be combined together. But since we have data, and since people, probably whenever they are writing the information in the form and all, they may get this kind of different data. Okay, so this kind of situation will arise. Similarly, if I go and see with respect to type of contract, so here you obviously have binary one, so you don't have to worry about it much. Now, there's 2 columns with respect to categories. I found out this specific mistake. You can definitely check out all the other categories also. It won't be there was nothing as such, but definitely I want you all to do this specific task with respect to other categories. Now we'll try to fix this. What we'll do, this female and this female, we'll try to make it as only one field, only as one category, and similarly single and unmarried as another category. So to do this, I'm just writing df of gender is equal to df of gender dot replace wherever this value is there. I'm just going to replace it with female. Okay. So and similarly with respect to marital status, I'll use single and unmarried. I'll just try to replace single with unmarried, so that only one type of columns exist. So once I execute this, the status has been updated. Now if I probably go and see df dot head, you'll now be able to see, probably if you execute this also, right, you'll be able to see again. So let me just execute after this. You'll be able to see. Now you'll be only getting male and female. Perfect. So we have done that issue. First issue is that about the spelling mistake, you really need to take care. Now is the most important feature, that is checking missing values. Now this is super important because see, missing values can occur due to many conditions. Okay, there may be randomly some missing values. Probably the user may not have entered that particular value due to some of the, they don't want to disclose that particular information. Now we will try to find out all the features with nan value. Okay, in order to do that, you see this. This is very simple. I'll say for feature in df.columns. I'm taking each and every columns. If df of feature dot is null dot sum is greater than or equal to 1, okay, not greater than or equal to 0. Here I have taken greater than or equal to 1. That basically means at least one nan value is there in that specific column. All those columns will be stored in this variable, that is features underscore with underscore na. Very much clear. Okay. Then for feature in feature underscore with underscore na, here what we did is that we are basically trying to find out the missing values, and based on that we are doing the mean and we are multiplying with the 100%. So in short, I'm going to get the percentage of the missing values, okay, along with the entry dot round. So I've taken each and every feature over here with respect to this nan values, and then we are just doing dot is null dot mean multiplied by 100. That basically means I will be getting this in the decimal percentage manner. So once I execute this, here you can see age is basically having 4.623% of missing value. This is having 0.51. This is having 5.13. This is having 1.92, 0.51, 531, 2.86, 1.35, 4.76. Okay. Now these are the basic things, okay, with respect to the nan. So now obviously you can see the percentage of missing values. Now let's say I also want to see the describe. Describe basically means what is 0 percentile, 25 percentile, 50 percentile, just to see that whether my data has some kind of outliers or not. Obviously with this you'll just not get the entire information, but definitely some basic information you'll be able to get it. So once I execute this, here you'll be able to see with respect to age. Now see, I've taken this features in nan value only, and I'm checking the information with respect to nan value only. Okay, sorry, features which are having nan values. Only those information I'm trying to check with respect to mean, standard deviation, minimum, 25 percentile, 50 percentile, 75 percentile, and max. And from this information, you can definitely see that if you compare with respect to 50 percentile and mean, there is hardly any difference. 50 percentile is the 50th percentile value, which is greater than the entire 50% distribution. Okay, so here you can see that okay, not much difference is there. Okay, similarly over here also you can see that much difference is not there. Much difference is not there. So this basically indicates that okay, you may have outliers, but it will be very less. Okay. So in this particular scenario, in this data set, right, the efficient way of replacing the nan value is we will try to impute median value for each column, because if in age outliers are there, median will take care of that. In terms of any categorical feature, if there are any nan values, okay, we will try to replace with or impute with mode. With respect to any integer values or float values, we'll try to use median. So median, mode. Okay, so this is the concept that we have applied. There is also some different ways where we will try to discuss that when we're discussing completely end-to-end project, and that will completely make sense because we have to also see the distribution, how the data is, and probably if transformation is also required, we have to do it. Okay, so right now I did this. So here all these things with respect to median, here we are replacing in age. So you can see df.age.fill na, df.age.median, in this is equal to true. Similarly, df.type of contact.fill na. So here you can see I'm using mode, right? Mode of first element, and I'll be able to get the mode element for with respect to categorical feature. Then similarly over here median, over here mode, wherever category features are here, I've used mode, and wherever okay, with respect to number of trips, you can basically see we have just wherever the values is not there, we have just replaced it with 0. But I could have thought that okay, this would have been fine. Let's go ahead and replace with median. So here I will just write df dot number of trips dot median. Okay, so here you can see dot median with function. So formula is there. Okay, so once I execute this, now this entire replacement will happen, and then you'll be able to see this value. Perfect. This is got executed. Now if you probably go and see df.head, now you'll not be having any nan values. Okay, so here it is. Okay, and probably if I also write df.isNull.sum, you will also not be able to see anything. So right now you have zeros. Now what I'm going to do in df.head, you have a feature which is called as customer ID. Customer ID is not that important, so I'm just going to remove this. Okay, to begin with. So here I'm just dropping customer ID in places equal to true and x is equal to 1. I think we have solved so many different examples. Okay, now there is some amount of feature engineering we'll definitely do this, because when I was observing the data, we can do really amazing things over here. Okay, and one thing what I found out in this specific feature, let's say I'll just go and write df.head. Okay, so here you'll be able to see that there was something called as, there's two features. One is number of children visiting, and there was number of person visiting. So here you'll be able to see one more feature, number of person visiting. Now, instead of having these two features separately, why can't I just combine these two features and create a derived feature where I just add this two feature? That would have been a good idea, right? Because our main aim should be that we should try to reduce the number of columns. And unnecessary two columns are there. If I add it up, then the total number of people I'll be able to see, right? So that is the reason. What I did is that I basically create df total visiting. Here you can see df number of person visiting plus df number of children visiting. When I add this value, I'll be getting total visiting, and then I'm dropping the column of number of visiting and number of children visiting, because no, I don't require that specific column again. Okay, so once I execute it, here it has got executed perfectly. Now you'll be seeing that two columns have got reduced, and one column has got added. That is total visiting. Perfect. So this is an amazing thing to do whenever you find. So that is the reason you really need to check each and every columns and what importance it is basically playing. Now let's go to the next one. Here I'm going to get all the numeric feature. Now how to get the numeric feature? All I have to say that feature for features in df.columns. This is the list comprehension. If I probably write if df of feature dot data type is not equal to object, O basically means not equal to object, then I am going to basically consider that all in the form of numerical features. So once I execute it, here you can see number of numerical features is 12. Similarly over here, if I say d type is equal to 0, then I'll be getting all my category features. So here you can see 6 category features, 12 numerical features. And there is also something called a discrete feature. Now if you don't understand what is discrete feature, understand discrete feature are like, okay, it will be having some categories, but fixed number of categories. It may have 20 categories, it may have 25 categories, not more than that. Okay, and obviously it will be more than this category feature that we have. In this category feature, we may have 1 category, 2 category, 3 category within a column. In discrete features, we may have more number of categories, like 10 categories, 15 categories, 25 categories. Okay, so I definitely want to differentiate between category feature and discrete feature. So here I've written condition whenever I try to find out a feature dot unique. Unique basically how many number of categories are. If it is less than or equal to 25, I'll say that okay, it is a discrete feature. Otherwise, it becomes a continuous feature. Let me give you a very simple example. Okay. Suppose there is a data set which has pin code. Now in pin code, I may have 25 unique, or I may have 20 unique pin codes, and after that it is not going to repeat. So I'm going to make it as a discrete feature. Okay, so let's go ahead and execute this. So here you can see 9 number of features are discrete features. Okay, similarly continuous features, all you have to do is that if the feature is not in discrete features, I will probably get all the features over here. Okay, so here you can basically see this discrete feature, whatever features are not there, I'm going to basically take it from numerical features. See, here also I've taken numerical features, here also I've taken numerical features, but for all the other thing we have used df.columns. Numerical features only will get the continuous feature and discrete feature. So from the numerical feature, we have divided that into continuous feature and discrete feature. So once I execute this, the total number of continuous features are 3. Okay, now till here we have actually done the entire thing. Now we will probably start the train, test, split and model training. Okay, because this is super important with respect to thing. And there is also one important thing, because still we have not taken care of the entire category features. Because if I probably just go and execute over here, see in my df.head, okay, still I have so many category features and this is still not fixed. So again, this is the part of feature engineering that I will do in the part 2 of feature engineering. That is the next video. Yes, this was it from this particular video. I will see you all in the next video. Thank you. Bye bye. Take care. So guys, so we'll continue the feature engineering part 2, and in this part what we're going to do is that how many different types of categorical features we have actually got. We'll try to solve this with the help of column transformer, one-hot encoding and binary encoding, right? Now this is what we're going to do, because at the end of the day we really need to convert all this category feature into integer values, right, or some numerical values. So first of all, before applying anything, you just have to do plain test split. So over here you can see the entire input features except product taken, which is my output feature, is basically put in my x variable, and in my y variable here you can see that I've taken product taken. So if I probably execute it, and if I probably just go ahead and write x.head, here it is. You can see all the features over here, and this is my x data. I don't have product taken because that is my output feature over here. And similarly with respect to y underscore value underscore count, here you can see I'm having 3900 features that is saying 0, and 920 is basically taking the product. Okay, still you might be thinking, Krish, can this be an imbalanced data set? I'd still say that okay, you have good number of zeros and ones, and whenever I talk about ensemble techniques like random forest, like z-boost, gradient boost, right, these all perform well even in imbalanced data set. So that also we'll try to see as we go ahead. Then we'll just go over here and execute x.head. So this is there. After this, I'm just going to do the train test split also. Okay, so train test split, I'm taking 20% of data in my test data and random state is equal to 42. So once I execute it, here it is. I'm having 390,17 in my training data set, and same 978 data points and 17 columns in my test data set. Now is the most important step. Super important, and probably this is the most efficient way to apply this particular step. So here you can see category features like type of contact, occupation, gender, and all these things we have already, we can save this in category features. So everybody focus over here and see how we are handling the category features. So over here, first of all, I will say x underscore or x.select data type include is equal to object.columns. So when I say we're going to include objects, that basically means, so if I probably just go ahead and execute like this, x.info. Okay, so here you'll be able to see wherever is the category features, right, that are actually objects as a return type. Okay, the data type is basically object. So here you can see object, here you can see object, and all the features with respect to this you can see basically object. So what I'm actually going to do, x.select data type include objects.columns. So when I say dot columns, all the columns that are of object type will be able to see in category features. Similarly, numerical features, if I say instead of include, I say exclude. In select data types, you have a keyword which is called as exclude object. So once you exclude object, all the integer and float value, whatever are present, it will basically get saved in numerical features. Okay, very simple, very easy step. Scalar and one is column transformer. Now, what is column transformer? First of all, let's understand. Whenever you really want to handle category features or you want to do standard scaling, you are specifically doing that in a columns, right? Now, this column transformer is a kind of library or class. What it does is that any kind of transformation you give inside it, you can combine multiple transformation techniques. Now, in this particular case, I'm going to combine one-hot encoder and standard scalar. Standard scalar I'm going to apply on the numerical features, and one-hot encoder I'm going to apply on the category features, right? Because I have many categories. So for that specific case, I'm going to use this column transformer. One-hot encoder, obviously, you know that if I have multiple categories, it will basically create a one-hot encoded format for that particular data, which is required so that the model will be able to understand. Similarly, standard scalar, I hope everybody knows it. Why we have to do it? We have to scale down the data in the same scale. And in random forest XGBoost also, we don't need to perform the standard scalar compulsory. Okay, here I'm just showing you because I want to show you the application of column transformer. Okay, that is the reason why I'm showing you over here. So let's go ahead and initialize standard scalar, which is numeric transformer, and here this is my variable, and one-hot encoder I'm going to initialize, and I'm using an important property which is called as drop is equal to first, so that if I just have binary categories also, it will do one-hot encoded. When it does one-hot encoded for binary, you get 2 columns. And always remember, the number of columns that is created by one-hot encoding, right? One column is not at all required. Suppose if there are n columns, then n minus 1 column will try to represent the entire data. Okay, so that is the reason I will be dropping the first column after I probably create one hot encoded. Okay, then I will go ahead and write column transformer. The first encoding that will basically happen is one hot encoder. I'm giving this particular name, and for this, the type that you'll be able to see in one hot, this is the variable type that you'll be able to see. Okay, so this is the object that I'm actually going to call one hot transformer, and where I need to apply this here in the category feature. So I'm going to assign the third as my category. This will be in a tuple format. Okay, and you can also go ahead and search in sklearn.com column transformer. So this is where the specific library is there, and one hot encoder and standard scalar is basically presented in pre-processing. So we are going to combine. See, since we are combining multiple transformer technique, we have to use column transformer. Then the second transformation is basically applying. The name is given as standard scalar. Standard scalar object is present over here, so I'm going to write object over here, and on which feature I want to apply, I want to basically apply a numerical feature. So once I do this and execute, my preprocessor will be ready. Now this preprocessor is nothing but it is a column transformer. So here you can see it is a column transformer with one hot encoding, and we are going to basically apply on all this particular feature. And similarly, standard scalar, we are going to apply standard scaling in all the specific features. Super important, super easy. Now let's go to the next step. Now obviously we have created this entire thing, right? The column transform here. Now we need to apply on the extra data. So let's go ahead and apply it on the extra data. Whenever you want to apply for a training data set. So here what I'm doing, I'm applying transformation in training data set. So whenever you want to apply transformation in training data set, this is a quick cheat sheet. You have to basically apply fit underscore transform. Okay, you have to probably apply fit underscore transform. So once I execute this, here you'll be able to see we'll apply it for the X twin. Now, if I probably go and see in the X twin, all the category features will get converted into arrays, right? So probably I can also make this as my pd.data frame so that you'll also be able to visualize it. So here you'll be able to see once I execute this is how all your category features have got created. And this is how your standardization has basically happened. Everything has basically got converted into category features. Now which column is what? You can definitely check out. You can probably see that with respect to the type of contract, occupation, gender will just have one column, right? Male and female. Male column will get deleted because you just need one column whenever there is a binary classifier because binary categories like zeros and ones. So this is how my training data set looks like. Now, similarly, for the test data set, whenever we need to apply the transformation, we just use transform function. Okay, why? Because of data leakage. Okay, we don't want to make sure that the model knows anything about test data. Okay, so here what we are going to do, we are going to apply transformation on test data by using transform. Okay, super important. Once I do this, my X test is basically ready. Okay, my X test is basically ready. Okay, so this is my X test. Perfect. I have my white training and white test. Now we are going to apply, or we are just going to write machine learning training. And this time I'm going to teach you something new. Okay, machine learning models training, or I can basically say random forest classifier, right? Random forest classifier training. So here I'm just going to make this as a markdown. And this thing I will start in the next video. So we have completed feature engineering 1, feature engineering 2, and this is how in this I really need to focus on how you can transform with the help of column transformer. Okay. So yes, I will see you all in the next video. Thank you. So guys, now let's go ahead and train our random forest classifier. So for that, I will first of all import random forest, and it is available in ensemble technique. And then we are going to import from sklearn.metrics. I'm going to import all the thing like precision score, recall score, F1 score, ROC curve, confusion matrix display, classification report, everything. Okay. And I will just try to execute this. Perfect. Now this is probably the first video where I'll show you an efficient way of training model. Now always remember guys, you cannot be just dependent on one model. You really need to try so many different algorithms, right? There's so many algorithms like classification, logistic, decision tree, and all, right? Similarly, in the further you'll be seeing execution, gradient, boost, and many more, right? So let's go ahead and see. With first of all, I'll just give you one example, and later on you'll be able to get an idea how we're going to train the model. Okay. So first of all, here you can see that I have created a key value pairs like this. Okay. Now key value pairs is basically my model. So over here, I've written random forest is equal to I've initialized random forest classifier by default parameters, whatever parameters are there. Now if I probably show you in sklearn random forest classifier, so here you'll be able to see that by default I have 100 decision trees. Okay, so whatever are the default parameters, just going to take this up and probably start implementing the random forest classifier. And later on we'll also try to see how we can do hyperparameter tuning. Okay, so by default I've taken this random forest classifier. Then for I in range of length of list of models. Okay, so that what I'm doing, I'm basically converting this dictionary into list, and I'm iterating through each and every values. Why values? Because here you can see I'm using model.values. So once I write like this, right, I will be able to pick up this particular information. This is key and this is values in dictionary. Okay, so first of all I'm getting the length of all the models that are over here. In this particular case I just have one model. Okay, so the length will be 1. So once I convert this length into list, and if I write of 1, this is indexing, then I'll be getting my first value. Why? Because I've used model.values. Okay. So once I do that, I'll be getting the model, then I do fit on train, and then I predict on X train, and then I predict on X test. And with respect to this, you can see I've used accuracy score, F1 score, precision score, recall score, ROC score. So everything is so simple. This is the training set information, right? And similarly, with respect to the test set information or performance, we're just going to calculate again all the things like accuracy score, F1 score, precision score, recall score, and ROC score. And here I'll be giving y test and y test correct, whatever we have actually calculated. Right? So here we are going to basically use this, and then I'm going to print all the models, whichever information we basically want. And then here you can basically see I'm printing the model information, and I'm printing with respect to the test information. Very simple. A simple model has got initialized, you have trained it, you have predicted it, and did many things. So here you have all the information. Okay, here you have all the information, and this is your model performance for training set, model performance for test set. Very simple, very easy till now. Here you can definitely see that I'm getting 100% accuracy for training data set. For test data, I'm somewhere getting around 92%, 93%, accuracy. But recall is very less. So obviously we need to also focus on hyperparameter tuning. Okay. Now you may be thinking, how to add other machine learning algorithm. Just add it over here. So if I probably write decision tree, okay. So I'll write decision tree over here, and I'll initialize decision tree classifier, and I'll import it over here. Right. This is the most efficient way of training the model. So I'm just going to import. I'm just going to write sklearn.tree import decision tree classifier. Okay. So here you can see that I'm just now initializing decision tree classifier. Okay. Now again, I've used key value pairs. Now see how many information I'll get. I'll get two information about, right? The entire algorithm. So once I execute it, here you can see decision tree model performance has got accuracy, and this is what I've actually got with respect to recall, and this is what I've actually got with respect to the other information of random forest, right? So like this, you can now add any number of algorithms. Like I can also go ahead and add logistic regression. Logistic regression obviously will have a low accuracy in this particular case because it tries to create a linear line. Okay. And here I'll again import another library from sklearn.tree, sklearn.linear model. And we have discussed about all these things, right? Logistic regression. Okay. So once I do this, I execute it. Now all I have to do is that initialize logistic regression over here. Again, this should be in the key value pairs. Now here you can see logistic regression accuracy is decreasing. The recall is also decreasing. Obviously over here from out of this thing, you can see that random forest is giving a good accuracy. So what I'm going to do, I'm going to take a random forest and do hyperparameter tuning. Now with random forest, we can play with multiple parameters. So in order to do hyperparameter tuning, again, you check n underscore estimator is there, criterion is there, you can play with criterion. We have discussed about all the thing in theoretical, minimum sample split, minimum sample leaf, all these features are there, and you can basically try it out. So that is what I've actually done over here. Max depth I've used, max features I've actually used. I've played with multiple parameters. N underscore estimator is like how many number of decision tree I can have, 100, 200, 500, 1000. So it is going to test from all these particular options. You can still add any number of options like you want, okay? You can keep on adding values, you can keep on adding numbers over here. That is not a problem. So once I execute this, so here is my entire parameters. And obviously, you know that we will try to create these parameters in the form of dictionary. And all these things we have actually executed, or we have also written line by line code. Then we are going to do hyperparameter tuning, and this time I'm going to use randomizer CV. Now in randomizer CV, I'm going to use something called as random underscore CV models. Here, the first model that I'm going to use is RF. The second, I'm going to give my model that is initialized, random forest classifier, and RF underscore params. So this is also an efficient way of hyperparameter tuning, right? Because see, over here, you can see that once I execute this, so what is my random underscore CV underscore models? So here you can see random CV underscore models. If I execute it, here is all the values, right? So I'm going to use this RF, random forest classifier, and this. So three important information in this tuple I'm getting. Okay. So I'm going to import randomizer CV. I'm going to take model parameters like this, and then I'm going to iterate through this random underscore CV underscore models, right? So random CV underscore models. So here what I'm doing is that I'm saying for a name, first of all I get the name, then model, then this second is the model, and third is basically my parameters. So I will be able to access the three information once I am iterating through this particular list, right? So this is my list. Inside this I have a tuple, and inside this I have three main information. And I'm getting that particular information. So once I get this information, all I'll do is that I'll apply my randomizer CV model. My model, I have to give it in my estimator, that is which algorithm I'm going to apply. And then I'm going to basically give my param distribution, which is nothing but this params, how many number of iterations I want to do, cross validation, verbose, and underscore job. And then we do fit on extend and white train, and then we get the best parameters. Okay. Once I get the best parameter, I'll be saving that in my model underscore param. Okay. So now if I probably execute this, so in short, this entire execution will happen in randomizer CV. The differences between randomizer CV and grid search CV is that randomizer CV will be a little bit quicker when compared to grid search CV. So this is going to take some amount of time because here we are going to do 3 folds and 100 iterations. So that basically means 300 total number of iterations and fits with respect to different combination or sample of combination of this. Okay. So now here you can execute. You have got this as your amazing thing. Like okay, you have got all these things. Okay. Here you can see the n underscore estimator is selected as 1000, minimum sample split has selected as 2, max feature has selected as 7. Now all you have to do is that again train this model by putting this value. So here I'm going to put it as 1000. Okay. And minimum samples that I will be putting is something like 2. So let me go over here. 2. Max features that you will be seeing is 7, and max depth that you're going to probably take is 1. Okay. So once I execute this, then again this entire same thing is copied, right? With respect to train, test, performance, accuracy, everything is same. So I'll try to execute it now. So this is probably taking some time to execute. Now here it is. Your accuracy is like this, and your test accuracy is something like this. And this is after hyperparameter tuning of your random forest, right? So before the result was something like this with respect to random forest, right? Recall was 67, and I think now recall has improved or not. It is somewhere around 67.02. Okay, but still we can try with different parameters and we'll try to check the performance. Okay, so this was the entire idea about how you can basically do the hyperparameter tuning and how you can even train multiple models. So finally, we'll also be plotting the ROC AUC curve. In this, I'll be using ROC AUC score. Again, I'll be defining my models. The label will be random forest classifier with all these features that I've actually defined in my random forest. So I'll just copy this again and paste it over here. Okay. And again, what is my AUC score? Go and see what is my AUC score with respect to test data 0.8325. So I'm just going to update it over here as 0.8325. And based on this, I'll be calculating my ROC AUC curve and then we'll be plotting this. I think this also things we have discussed completely. So now probably you'll be able to see the plot figure, which looks something like this, right? And by this, you can see that 83% of the area is basically covered by the random forest. Okay. So this was an idea about it. Now in the upcoming videos, what we are going to do, if you really want to discuss about XGBoost, then we will try to update this particular example with XGBoost, AdaBoost, Gradient Boost, and later on we want to quickly start also end-to-end project. So I hope you got an idea about model training with respect to random forest classifier. And this is an efficient way of training the model. We definitely can basically check like how many different types of things are there. Okay, and yeah, you can definitely try with any number of models that you want. Make sure that you check all the accuracy and then you come to a conclusion. So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys. So we are going to implement the random forest regression machine learning algorithm with the help of Python and sklearn. So here we are going to take up a problem statement like how we did it for random forest classification. And this particular problem statement is regarding car price prediction. So we basically need to predict the used car price prediction. Let's say a person wants to sell a car and company has this particular entire data and it should be able to predict based on various features what should be the car price. We'll talk about a lot of many features as such, but let's understand the problem statement right now. The dataset comprises using cars sold on cardeco.com in India as well as important features of this car. If user can predict the price of the car based on input features, prediction result can be used to give new seller the price suggestion based on the market conditions. So this is entirely the problem statement. Over here, if you see that the dataset is selected from scrapping from cardeco website, the dataset consists of 13 columns and 15411 rows. Okay. So if in short, we'll initially import all the libraries that we require. So let's say we go ahead and import this, and then when I have this particular dataset which is called as cardeco underscore imputed.csv, and if I use index column is equal to 0, we will be able to see the dataset. So this is how my dataset looks like. Okay, so here you can see I have independent features like car name, brand, model, vehicle age, kilometer driven, seller type, fuel type, transmitter type, mileage, engine, max power. There's so many features like seats, and then this is my output feature that is my selling price. So this is obviously a regression problem statement. So this is all about the problem statement. In this, in the upcoming videos, we'll be applying multiple algorithms other than random forest regression too. There are so many other regression algorithms which we have already completed. So this is about the problem statement. It is very simple. We really want to predict based on all this particular feature what should be the price of the car that we need to sell it. Okay. So yes, in the next video we'll talk about feature engineering and all. Okay, I'll see you all in the next video. Thank you. So guys, now in this video, we are going to perform the feature engineering. And the feature engineering, the first step is something called as data cleaning process. Handling missing value, handling duplicates, check data type, and we'll try to understand the dataset. Now, first of all, to check whether the dataset has any null values, we will basically write df.isNull.sum. So once we do this, here you'll be able to see that I'm having all the values as 0. Okay. So this is the function we basically use to check the null values. Very simple. And I think we have done so many videos and we already know how to do this. Okay. Now, from this particular data set, you can see that these three columns are saying or providing the same information: car name, brand name, and model, right? So over here, Maruti Alto, brand is Maruti, Hyundai Grand, then brand is Hyundai, and then again model is Grand, right? So instead of all taking all these three columns, I can just take one column, and according to me, the most important column will be the model, because based on the model only we can decide what may be the price. Brand can be repeated, car name can be repeated, right? But model can change, right? Based on different models can be there. So what I will do is that instead of taking car name or brand, I will just try to drop these two columns and we'll take model. Okay. So over here, what I'm going to do, I'm just going to drop car name, brand from axis equal to 1 in place is equal to 2. Okay. So let's go ahead and let's try to see this. Okay. Now we have df.head. If I see only model is remaining, vehicle age, and this all features are there. So we'll see how to handle category features and all. That is not a problem. Now if I probably go ahead and see what is df of model.unique, now here you can see all the different kind of models that we basically have, right? And for this also we have to do some kind of encoding, and I will prefer label encoding for this, and I'll tell you why I'll do that. Okay. Now coming to the next one, here we are going to see how many number of numerical features are there, how many number of category features are there, discrete features are there, continuous features are there. This is just to understand how our data set is, So obviously for the number of features, numerical features, I'll just write this condition: df of feature dot data type is not equal to O. O basically means object. And for this, I will be iterating for columns for feature in df dot columns. If df dot d type is not equal to O, I'm going to just take that particular feature and put it in number underscore feature. So this is basically my numerical feature. With respect to categorical features, here you can see the data type will be equal to obviously object. So here we'll be able to get all the category features. And then I have my discrete features. So discrete features here, I'm just saying that my number of unique categories will be less than 25. This will be the part of numerical feature. As suggested, I always discussed this previously also. In a numerical feature, there may be some features like pin code that may have fixed number of values, and if the number of unique values is less than 25, I can consider that as discrete feature. So that is the reason why I have used this discrete feature. And then continuous feature is again from the number of feature. Whatever is not present in the discrete feature, we are going to take this. So just try to execute this, and here you'll be able to see number of numerical features is this much, category feature is this much, discrete is this much, continuous feature is this much. Okay. Now let's quickly go ahead and divide our data set into independent and dependent features. And before doing this specific work, also I'll not do the let's divide this data set into independent and dependent feature. And I've already imported also train discrete so that in the future I can do it. So I'm removing selling price from the data frame. I'm putting that in my x independent feature. And over here you'll be able to see I'm taking the selling price and putting in my output feature. So here it is, and this is what is my x.head look like. Okay. So x.head is basically all my data that is present over here. Now coming to the next one. You can see over here we are performing feature encoding and scaling. And in feature encoding, since I have so many different categories, right? Like seller type, fuel type, transmission type over here, and this all are main the features, right? Over here, model, right? This all, see, model will definitely have many number of features, right? So what I will do, let's say I'm just going to write over here df of model, okay, dot unique. Okay. So if I probably do this, I'll be able to get all the unique values. And if I probably try to see the length of this unique also, you'll be able to get it, right? If I probably just write length of this unique value, here you'll be seeing 120 unique values are there within the model. Okay. And if you also probably see value underscore counts, that also you'll be able to find out, right? So if I execute like this and just write instead of unique, I will say value underscore counts. Okay. Here you have so many different counts. Okay. Now, usually for this type of problem statement, what we are actually going to do is that when we are solving this, right, model can play an important role with respect to the price. So what we are going to do is that we will try to transfer, we'll try to convert this into label encoding. We'll assign different labels for this particular model, for this data. Why I am specifically putting label values is that because understand, if I put a label value over here, it will try to find out the relationship between the selling price and this particular label itself. Because some of the label, let's say if it is very high, that price may be very high, or the price is very less. So that kind of relation I really want to find out in this specific data set. That is the reason why I'm taking label. Otherwise, what I can do is that which is the most frequent top 15 elements, I can take that and I can assign different labels. For the remaining one, I can assign it as others. Okay, and probably assign a different label for that. So something like this we can basically do. So this is the one thing we'll try to assign label by using label encoding. Now in order to do this for model, what I'm doing from sklearn.preprocessing, import label encoder. Now label encoder is a technique which will actually help us to assign labels. So if I probably give label encoder like 0, 1, 2. So let me also show you what does label encoder basically do. If I write sklearn label encoder, okay. So here you'll be able to see this will just assign labels. Now to see for this, when we do fit on 1, 2, 2, 6, then it's just going to assign the label like 0, 1, 2, right? So when we are transforming this, right, here you can see 1, 1, 2, 6 is nothing but 0, 0, 1, 2. So 2 is basically assigned the first label, 6 is assigned the second label. So we're just going to assign the label based on the number of categories over here. So this is what we do. First of all, we import label encoder, and then we just write fit underscore transform on this particular value. So all that model will get updated. Now probably if I go and just search for or just type x.head, you'll be able to see I'll be having label values. Don't do it one-hot encoding. See, one-hot encoding also people may think we can do it, but again, it is just going to create 120, 119 extra columns. Okay. I really want to find out the relationship between model and this output value. That is basically y. Okay. When we are training our model. Now, still we have seller type, fuel type, and transmission type. So what I'm actually going to do over here. Okay. I will just write something very important. Okay. Not very important. Whatever we have written over here. So let's say I'm just going to copy this and probably just paste it over here. And instead of writing model, I will just say seller type. Now here you'll be able to see that we will be having unique categories, like only three categories are there. For these 3 categories, and then again, if I probably copy and paste it with respect to the other category over here. Okay. Fuel type. So here also you'll be able to see 5 categories. Then we will try to do it with transmission type. Okay. So transmission type here also you'll be able to see transmission underscore type. Here you'll be able to see only 2 categories are there still, right? So for all these things we can do one-hot encoding because the number of categories are very, very less. Okay. So let me remove this label encode. I don't require it over here. So here you can see numerical features. I'm going to apply 2 things now. One is standard scaling. This is not compulsory again whenever we apply random forest or any assembly technique, but just to show you how the column transformation takes place, how we can apply multiple transformation technique within a pipeline. I'm showing you this. Okay. So first of all, I have my numeric columns over here. All I have to do is that select the data types, exclude all the objects. And then one-hot columns, which are my one-hot columns. So here you can see seller type, fuel type, transmission type, right? So seller type, fuel type, and transmission type. And then I'm saying from sklearn.preprocessing, import one-hot encoder, standard scalar. This both I'm going to apply inside my column transformer. Okay. So I don't require. Okay. So then we initialize standard scalar as numeric transformer and one-hot encoder. We drop is equal to first as one-hot transformer. Then I'll say column transformer. Then first apply one-hot encoder. Then apply standard scalar, and we can apply any number of transformations that we want. And this is a very important feature which we say it as remainder is equal to pass through. This basically means that it says that okay, other than this particular feature, we don't have to delete any of these features. So these features will be kept like that only. Only those features that are basically having this categorical features, we are going to just keep it like that. Only that will change, and remaining all the features will be kept like that. So that is the reason we write this particular parameter which is called as remainder is equal to pass through. There is also one more parameter we can use for this, but if I don't give anything, then it is just going to delete that feature. So here is what I will execute it. So this is got executed. Now all I have to do is that do the fit underscore transform on X. Now if I probably go and see my X, you'll be able to see all my features are done. So if you really want to see in detail with, I can use data frame on this X value. So here you can see all the features I got transformed, and we have also got it as categorical encoding. At the end of the day, I'm just getting 14 columns, which is very good. Initially, if you see how many columns we had, so if you probably see df.shape, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 13 features, but we remove 2, 3 features, and at the end of the day, after doing all these things, you can see I'm able to get only 14 columns, which is very good with the help of one-hot encoding. Again, I use drop is equal to first, that means first column will always be dropped after the one-hot encoding is done. Then we are doing train test split, so this is my X-train, okay? Then all together, now is the time which we will be saying that we'll apply model training, okay? So I hope you have understood this feature engineering. We did this train test split and how did we encode all the category features and all. So in the next video, we will try to do the model training, and then we'll also select the model. Thank you. I will see you in the next video. So guys, now in this video, we are going to do the model training and model selection. And this is with respect to random forest regressor. But here I have also used linear regression, ridge lasso, k nearest neighbor decision tree regressor, because all these things we have already discussed. Now, one important thing is that guys, see, initially, how do you select a model? First of all, you train all the model, all the regression model with respect to the dataset that you're giving, right? Now in this particular case, I'm going to just use all these models that I've actually imported. Along with that, I'm using all the metrics like R square, mean absolute error, mean square error. Okay. So once I do this, and probably once I execute it over here, so this is what it has got executed. And I'm creating a function which is called as evaluate model. Here, I'm going to give my truth value and predicted value, and we are going to compute the mean absolute error, mean square error, and NP dot square root with respect to RMSE. And then I'm also going to compute R square. So all these values will try to provide over here, return this particular value through this evaluate model. So this is one function. Now the same method, whatever we did in random forest classifier, the same thing we are going to do. First of all, we are going to create a key value pairs like linear regression, lasso, ridge, k nearest neighbor, and here we are initializing it, right? We are initializing. And this is all a regression problem shape. Then I have decision tree regressor, random forest regressor. All these things are there. Now what I'll do, I will just iterate for each and every model, do the fit train on my train, make prediction for the train, make prediction for the test, right? Then I'll evaluate the model with respect to MAE, RMSE, and R square. How? By calling this evaluate model and giving my y train and y train paired. Okay. Similarly over here, y MAE, RMSE, R square. Here I'm going to give it y with respect to y test underscore red and y test. Okay. Then I'm going to check the model performance for the training dataset and model performance for the test dataset. Okay. So that is what we have actually done. Very simple, no much complexity. But we are just doing this. Okay. Now if I go and execute, now here you'll be able to see linear regression. Let's focus on R square right now. I got 62% for train, test 66. Here 62%, 66. Okay. Ridge, I got 62. And 66. But what about k nearest neighbor? I got 86 and 91. This is good, right? This is good. Now we are improving things. Then I got decision tree 99 and 87. So anyhow, it is less than test data accuracy. And then random forest is 97 and 93. So out of all these things, you can see random forest is performing superbly well. And then you also have k nearest neighbor, which is performing superbly well. So I'm going to select this both the model and now perform hyperparameter tuning. Now again, I'll be trying with different neighbors and random forest regressor. If you probably go and search for scale on regressor, random forest. Okay, you will be able to find all the information. So here it is. If you go and just play with this all parameters, whatever parameters we have discussed in the theoretical discussion. So this values, there are a number of estimators can be different decision trees. Match that with the other values, min sample, max sample, min weight, max features, everything. We can play with these parameters, and that is the reason why we have written all these things. Right? You can add still more parameters. Here I'm just showing you an example with respect to 4 different parameters, and I've assigned different values. In k nearest neighbor, I've used neighbors like 2, 3, 10, 20, 40, 50. So out of this, it is going to do the check. Right? Then like how we created all the models over here with respect to key value pairs. Here also what we are going to do. Here we are going to set it with respect to tuples. Okay. So here will be my model name. This is my model, and these are the parameters that I need to play with. Here is again my model name. Here is the model initialized, and these are the parameters that I need to play with it. So here is all my random underscore CV model, and then I'm going to apply randomized CV. This is for hyperparameter tuning, right? So this I'm just going to write it for hyperparameter tuning, right? So once this hyperparameter tuning is done, like for name, model, params in random underscore CV model. So I'm going to read this, this, and this. So here I'm going to get my estimator is equal to model. I'm going to apply my parameters, and underscore iteration is 100, cross validation is 3, purpose is equal to 2, and underscore jobs is equal to -1. And then I'm fitting my X-train and my train, and then I will be putting my best params, and here I will be able to get my best params. Okay. So let's execute this. Probably it'll take some amount of time because it is going to do this many number of fits with respect to randomized forest, right? So 3 folds for each of the 6 candidates. So here you can see all the things that are basically happening, and this is going to probably take some amount of time. The time is also shown over here. How many seconds is getting worked? How many concurrent workers are working? And obviously I have a very amazing system. So it will be able to give me the output quickly. But anyhow, we'll just wait. But after this, again, whatever best parameters I'm going to get, I'm going to upload it over here, and I can train the model, do the same step, and finally get the performance over here. Okay. So I think the execution will get over now, and I'll get my best params. But this is amazing, right? Now you can probably take any data set. You know how to handle category features. You know how to handle missing values. You know all the steps. Now you just need to apply those steps. Follow the best thing. Now see, with respect to KNN, I got 10 neighbors, right? With respect to random forest, I got 100 estimators. So I'm going to update over here. Minimum sample split is 2. I got over here. Max underscore feature is nothing but auto. So here I'll just going to write auto, and then max depth is none. Okay, and underscore jobs is equal to 1. This n underscore neighbor is equal to 10, and underscore jobs is equal to -1. So I'm just going to apply over here with the same thing and do all the same step again. Calculate our training accuracy and test accuracy. So once I execute this, now this is how I'm getting 98% and 93%. And k nearest neighbor is 83 and 90. Right. So these are the top 2 models we can use. One is random forest regressor and one is k nearest neighbor. Now in the upcoming examples, what we're going to do, guys, let's say if you want to do it for gradient boosting, you can just add that gradient boost algorithm over here, and we can continue it. Okay, and that kind of methodology I'll follow when I'm training this particular algorithms. So yes, this was it from my side. I'll see you in the next video. Thank you. In this video, we are going to discuss about the ADA boost machine learning algorithm. In a previous video, we have already discussed about 2 ensemble techniques. One is called as bagging and boosting. In bagging, we have covered the machine learning algorithm, which is called as random forest classifier and random forest regressor. So now we are going to move towards boosting algorithms. Now in boosting, we are going to start with ADA boost, then we are going to see gradient boosting, and then we are going to see XG boost. Remember one thing, guys, with both this bagging and boosting, you'll be able to solve both classification and regression problem statement. Now to start with, one more important point is that all this algorithm uses decision trees as a base learner or weak learner. Whenever we are talking about boosting, we basically say something called as weak learners over here, and here in the bagging technique, we use something called as base learners. And then all these things we will be using decision tree as our base machine learning algorithm or model. Okay. Now let's go ahead and let's quickly discuss some of the important or revise some of the important points. Now in decision tree, guys, we know that if we are trying to create a decision tree to its complete depth, right? So if you are trying to create a decision tree, let's say to its complete depth. Now in this scenario, what will happen is that in this scenario, you will be seeing that, okay, fine. Let's say if I'm creating this particular decision tree to its complete depth. In this scenario, it usually leads to something called as overfitting. Now, whenever we say overfitting, that basically means our training accuracy is very high, right? But our test accuracy is very less, right? So during this particular scenario, we have a condition. If our training accuracy is very, very high, we basically say it as low bias. And if my training test accuracy is very less, then we basically say this as high variance. Now, as we went towards random forest, right? In random forest, what we have multiple decision tree, right? In random forest, we have multiple decision trees. We use multiple base learners like decision tree. So the question that people may ask you is that, or interviewer may ask you is that, if decision tree is there, why do you use random forest? And I've already explained you, in random forest, since we are using multiple base learners, right? Suppose I have a data set, I will be providing a sample of data set to multiple decision trees, and those are my base learners. Here, what we do is that we try to convert this low bias and high variance to something called as low bias and low variance, right? How do we convert this into low variance, this high variance into low variance? Since we are using multiple base learners and we are giving sample of data set for training of that specific model. Now, this random forest technique that we were using is something called as bagging technique, right? And in bagging technique, we use base learners. Now, if I go to boosting, then boosting, what happens is that we try to create from this particular data set, let's say this is my data set, we create a weak learners, right? Suppose this is my decision tree, we create something called as weak learners, right? So this weak learner, let me just not draw this decision tree right now. Let's say that I'm going to use multiple models. Let's say this is my decision tree 1. Then I will be using all these models sequentially. I'll be connecting this particular model sequentially. And what we do in boosting technique is that whatever records have been wrongly answered over here or wrongly predicted, we send that particular records to this particular decision tree. Similarly, from decision tree 2, whatever records we have wrongly predicted in decision tree 2, that we send it to the next decision tree. Like this, all the models are sequentially connected. Okay, sequentially connected. And here, for this models, we say something called as weak learner. And if I combine all these weak learners sequentially, final thing that we are going to get is something called as strong learner. Okay. So usually in the case of boosting technique, what does weak learner basically mean? Weak learner basically means that these models have not been trained properly with the training data set. That basically means this weak learner haven't learned much from the training data set. So guys, now you already know that in random forest, suppose if you are going to consider random forest, and in case of classification algorithm, we use something called as majority voting classifier, right? Majority voting classifier in the case of classification problem. That basically means after training our model, whatever will be the output from all the models, we will basically do the majority voting and we'll get it. Similarly, in the case of regression problem, we basically find out the average of all outputs, right? Now, with the help of AdaBoost will not work like this. In AdaBoost, we assign some weights. We assign weights to this weak learner. This is the most important thing in AdaBoost. Whenever you use boosting technique, that is sequentially connected technique, we cannot go with maximum or majority voting classifier. Instead, we focus more on assigning higher and lower weights. Everything will make sense as we go ahead. But just let me tell you all the important points with respect to AdaBoost. Okay. So if I really want to create a AdaBoost function, the function will look something like this. F is equal to alpha 1 multiplied by model 1 plus alpha 2 multiplied by model 2 plus alpha 3 multiplied by model 3, like this up to alpha n multiplied by model n. Here, m1 to mn are my decision trees stubs. I'll talk about what exactly stubs. Okay, just let's consider that m1 to mn are my decision tree stubs. Now this alpha 1, alpha 2, if I probably talk about this alpha 1, alpha 2, alpha 3 up to alpha n, these are my weights. Which weights I'm actually talking about over here. These are the weights that are assigned to my weak learner, because these are also my weak learner, this is also my weak learner, this is also my weak learner, this is also my weak learner. And based on this particular function, we try to solve both classification and regression problem. Now, one very important thing that probably we have discussed, right? Say in random forest, I already have low bias and low variance. Now, suppose let's go ahead and discuss about AdaBoost. What is this decision tree stump? Decision tree stump basically means here we are going to create a decision tree whose depth will be just one level. Okay. So suppose if this is my decision tree stump 1, this will be my decision tree stump 2, and we are going to connect this decision tree sequentially. Okay. This decision tree sequentially. Like this, any number of decision tree we will be having. And this decision tree is basically called as a stump. What does stump basically means? That the depth is just one level depth. Okay. Nothing more than that. So that is the reason, obviously, if you see that, if my decision tree basically have just one depth, then this can definitely be considered as a weak learner. Whenever I have a weak learner, this basically leads to underfitting, right? Underfitting. Now, whenever I have underfitting, what does this basically mean? This basically means that my training accuracy is less, and there may be a scenario that my test accuracy may be more or less. Let's consider that it is more, right? But your training accuracy is very less. Okay. If I probably say, if my training accuracy is 40%, let's say my test accuracy is 45%. Now in this scenario, your test accuracy is more than your training accuracy, right? But here your training accuracy is very, very less. If this was somewhere around 90 and 95, I would have been very happy, right? But over here, since our weak learner is just for one depth, we can definitely say this is actually underfitting the conditions, right? So usually, initially in this particular decision tree stump, what we have something called as high bias, because whenever we talk about bias, we're basically talking about training data, and then we have something called as low variance. Right? Now, when we combine multiple decision tree stump like this sequentially, when this all are basically combined together, then this will in short lead to something called as low bias and high variance. Right? So in short, if I'm connecting all this sequentially together one after the other, this entire combination will basically be leading you to low bias and high variance. Initially, with the help of decision tree stump, we were getting high bias and low variance. Right? Now let's go ahead, because here I just told you what exactly AdaBoost is basically happening. In AdaBoost, what exactly is happening? We are just creating weak learners. Why do we say this trees or this stumps as, or I can also say decision stumps, right? This stumps as weak learner because it just has a depth of 1. But when I combine all together, if it has just a depth of 1, and this if independently, if we are trying to do some prediction, it will lead to overfitting, right? Overfitting basically means high bias and low variance. But if I try to combine all this decision tree stump along with weights, okay, because here we will be, as I said, we are going to assign some weights, right? When we combine this, we are going to get low bias and high variance, okay? Now in the upcoming video, we are going to see how we are going to solve this AdaBoost. Are we going to understand the maths intuition, okay? How does AdaBoost actually work, okay? And when we understand once how the AdaBoost will actually work, you'll understand how the boosting technique actually comes up in solving any classification and regression problem. So yes, I will see you all in the next video. Thank you. Now, previous video, we have got a brief understanding about AdaBoost and what is the main aim in AdaBoost. We'll try